It is passing through you right now. Billions of particles every second, moving at hundreds of kilometers per second, passing through your body, through the bed beneath you, through the floor, through the rock and iron of the planet, and out the other side without slowing. You cannot feel them. No instrument you can hold in your hand will register them. They give off no light, no heat, no charge. They interact with ordinary matter so rarely that a single one of them could travel through a light year of solid lead and emerge on the far side untouched. And without them, none of this would be here. No galaxy, no sun, no planet with a person on it, lying in the dark, listening. Of all the matter in the universe, the material that has mass, that gathers, that builds structures, only about 15% is the ordinary kind. The protons and neutrons and electrons that make up you, and the chair, and the stars overhead. The other 85% is something else. We have mapped where it is. We have traced its influence back across 13.8 billion years. We know how much of it exists to within about 2%, which is a better measurement than we have for the mass of the Earth's own crust. And after 90 years of looking, we still do not know what it is. Hello, and welcome to Sidereal. This is a channel about space, what we know, how we came to know it, and what has refused to yield. Tonight we are going to spend a long time with the largest unsolved fact in science, that most of the material universe is invisible, and that everything visible is a thin layer of decoration on top of it. Before we begin, if you find this kind of slow exploration useful for sleep or for winding down, a like or a subscribe genuinely helps the channel. And I'm always curious where you are listening from. Drop your location and the time in the comments. It is a small ritual I have come to enjoy. Here is the question I want to keep in front of us for the next few hours. How do you come to know the weight of something that has never been seen, never been held, never been caught in any instrument built for light? Not guess at it, know it, to 2 decimal places. By the end of tonight, you will have followed the whole chain, the spinning galaxies, the bent starlight, the ancient afterglow of the first fire, and you will understand why the answer at the end of that chain is still missing. Let us begin close to home. With the room you are in, the local density of dark matter, here in the plane of the Milky Way, is roughly 1/3 of a proton mass per cubic centimetre. That is the number astronomers arrive at when they measure how stars in the solar neighbourhood move up and down through the galactic disk, and ask what weight is pulling them back. In a bedroom of ordinary size, say 50 cubic metres of air, the total dark matter present at any given moment amounts to something in the region of a few tens of trillionths of a trillionth of a kilogram, the mass of a virus particle. You could sweep together every scrap of dark matter in a city block and it would not outweigh a grain of sand. That sounds like nothing, and locally it very nearly is nothing. But dark matter is not distributed the way air is distributed. It does not fill a room evenly and stop at the walls. It pools. It gathers into enormous, roughly spherical halos around galaxies, and those halos are the largest coherent objects in the universe. The halo of the Milky Way extends outward to something close to 1,000,000 light-years, roughly 10 times the diameter of the visible disk of stars, and far enough that it very likely brushes against the halo of Andromeda somewhere in the space between us. Its total mass is around 1,000,000,000,000 times the mass of the Sun. The stars, the gas, the dust, every nebula anyone has ever photographed, all of it together, is a thin frosting on the surface of that invisible weight. Now consider what that means for the room again. If dark matter is made of what physicists call weakly interacting massive particles, heavy things, perhaps 100 times the mass of a proton, then something on the order of 1,000,000 of them cross through your body every second, each one carrying the mass of a small atomic nucleus. Not one of them disturbs a single cell. If instead dark matter is made of the much lighter candidate called the axion, the count is not 1,000,000. It is hundreds of trillions per second, every second, for your entire life. Because a lighter particle means more of them are needed to add up to the same measured density. You have never once been outside that flow. Neither has anything else. There is a direction to it too. The sun is not stationary inside the halo. It is moving through the galaxy at roughly 230 kilometers per second, dragging the whole solar system with it, and the dark matter of the halo is not rotating with the disk the way the stars are. The halo is a slow, roughly random swarm. So from our point of view, we are driving into it. There is a wind. It comes from the direction of the constellation Cygnus, which sits near the point on the sky that the solar system is currently heading toward. If you could see dark matter, and if you stepped outside tonight and turned to face Cygnus, you would be facing into a headwind of it, blowing at a few hundred kilometers per second, and you would feel nothing at all. That wind has a season. In June, the Earth's orbital motion around the Sun adds to the Sun's motion through the galaxy, and we sweep through the halo slightly faster. In December, 6 months later, the orbital motion subtracts, and we sweep through slightly slower. The difference is small, a few percent, but it is real and it is calculable. And as we will see later tonight, one experiment has spent more than 20 years claiming to have detected exactly that seasonal rise and fall, while every other experiment on Earth has failed to confirm it. The strangeness of dark matter is not only that it is invisible, plenty of things are invisible. The air in your room is invisible. Radio waves are invisible. The strangeness is that it refuses to do the things matter does. Ordinary matter is sociable. It collides. It sticks. It radiates away energy when it is compressed, which allows it to cool, and cooling is what allows it to fall inward and settle and flatten. That is why the solar system is a disk. That is why galaxies have spiral arms. That is why gas can collapse far enough to ignite a star. Every structure you have ever seen exists because ordinary matter can shed heat and pull itself tighter. Dark matter cannot do this. It appears to have no way of losing energy. It does not radiate. It does not collide with itself in any way we have been able to measure. Two dark matter particles crossing paths simply cross paths. So it never cools, never settles, never flattens. It cannot form a disk. It cannot form a planet. It cannot form a rock or a molecule or a single grain of anything. It stays diffuse, forever, moving on its own orbits through the halo, passing through itself and through everything else as though the universe it occupies were not quite the same universe as ours. There are no dark stars. There is no dark chemistry. There is, oh dark anything, just a vast, slow, structureless weight that holds galaxies in shape and does nothing else. And that leaves exactly one way to study it. Gravity is the only force it cannot avoid. Everything else, light, magnetism, the strong nuclear force that binds a nucleus together, whatever it is that makes a table solid enough to lean on dark matter simply ignores. But nothing ignores gravity, and nothing can be shielded from it. There is no material you can put between two masses to reduce the pull between them. Gravity leaks through everything. So the method is this. You do not look at the dark matter. You look at what it is doing to things you can see. You measure the motion of what is visible, and you ask what weight is required to produce that motion. It is the oldest technique in astronomy, older than the telescope in principle, and it is how every measurement of dark matter that exists has been made. Not one of them is a direct observation. Every one of them is an inference from a moving thing, which means the entire subject rests on a single quiet assumption that when something moves, we know what is pulling it. The first person to notice the discrepancy was not Fritz Zwicky, though Zwicky is the one who gets the credit and who earned it with a far bolder claim. It was a Dutch astronomer named Jan Oort, working at Leiden in 1932. Oort was studying how stars near the Sun move perpendicular to the plane of the galaxy, bobbing up out of the disk, slowing, falling back through it, overshooting, coming back again, like weights on a spring. The frequency of that oscillation depends on how much mass is spread through the disk. Oort measured the bobbing, calculated the required mass, and found more mass than the visible stars could account for. He did not call it dark matter. He assumed it was faint stars and cold gas that had simply not been counted yet, which was a reasonable assumption at the time, and turned out to be largely correct for that particular measurement. Modern data has narrowed the Oort discrepancy considerably, but the shape of the argument was already there. In 1932, a motion measured, a mass calculated, and a gap between the mass and the light. 1 year later, and 8,500 kilometers away, someone applied the same logic to an object 1,000 times larger, got an answer 400 times too heavy, and published it anyway. Nobody listened for 40 years. In the constellation Coma Berenices, high above the plane of our own galaxy where the dust thins out and the view opens onto deep space, there is a swarm of more than 1,000 galaxies bound together in a single gravitational knot. It stretches across roughly 20 million light years. Its light has been travelling for about 330 million years to reach us, which means the Coma cluster you can photograph tonight is the Coma cluster, as it was when the first reptiles were spreading across the supercontinent. Through a modest telescope, it is a scattering of faint smudges, easy to mistake for flaws in the optics. Each smudge is a city of stars. Some of them contain more than 1 trillion. In the early 1930s, astronomers had just acquired the ability to measure how fast those smudges were moving. The technique was the Doppler shift, the same effect that raises the pitch of an approaching siren and drops it as the siren passes, applied to light instead of sound. A galaxy moving away from us has its light stretched slightly toward the red end of the spectrum. A galaxy moving toward us has its light compressed toward the blue. A galaxy moving toward us, the dark absorption lines in a galaxy's spectrum, produced by specific elements at specific wavelengths, act as fixed reference marks. Measure how far those marks have slid, and you have the galaxy's speed along your line of sight in kilometers per second from a photograph. Vesto Slipher at the Lowell Observatory in Arizona had pioneered this work, spending years at a telescope taking exposures so long that a single spectrum could occupy several nights. By the early 30s, there were enough measurements of galaxies inside clusters to start asking a structural question. How fast are the members of a cluster moving relative to one another? The expectation was modest. A cluster is an old, settled place. The galaxies should be drifting around one another at perhaps a few hundred kilometers per second, held in a loose gravitational bowl by the combined pull of all the stars they contain. The measurements said something else. The galaxies in Coma were moving at 1,000 kilometers per second, some faster. At those speeds, a galaxy could cross the entire width of the cluster in a few 100 million years, a single lap in the time it takes the Sun to make 1.5 orbits of the Milky Way. If the cluster had existed for billions of years, and every indication was that it should have evaporated. The galaxies should have scattered into the general expansion of the universe long ago, leaving nothing behind but a thin trail. Instead, there it sat, dense, symmetrical, obviously old, and obviously still bound. The tool for turning that observation into a number is called the virial theorem, and it is not a modern invention. It comes from the 19th century, from the study of gases, where it was used to relate the motion of molecules in a container to the forces holding them there. The theorem applies to any stable system of objects moving under their own mutual gravity, a star cluster, a swarm of galaxies, a box of gas. It says that for such a system to be in equilibrium, the energy of motion and the energy of gravitational binding must sit in a fixed ratio. Loosely, how fast things are moving tells you how tightly they are held. Measure the spread of speeds, and you can calculate the total mass that must be present to prevent the whole arrangement from flying apart. It is a scale. It weighs objects the size of a cluster of galaxies using nothing but the motion of their contents. The man who put the Coma cluster on that scale was a Swiss astronomer at the California Institute of Technology named Fritz Zwicky, and he was, by a considerable margin, the most difficult person in 20th century astronomy. He had arrived in Pasadena in 1925 on a fellowship from the Rockefeller Foundation, intending to work on the physics of crystals. He occupied an office on the second floor of the Robinson Laboratory of Astrophysics, a building with a dome and a long, quiet corridor. He was tall, broad through the shoulders, and he kept a heavy Swiss accent his entire life. Somewhere in the first few years, he turned his attention upward and never turned it back. By the early 1930s, he was producing some of the most original work in astrophysics. In 1934, with Walter Baade, he coined the term supernova, proposed that supernovae represent the transition of an ordinary star into a neutron star, and suggested that they were the source of cosmic rays. 3 ideas, all correct, all decades ahead of the observations that would confirm them, all in a single short paper. He was also, by universal agreement, impossible. He referred to colleagues who disagreed with him as spherical bastards, on the grounds that they were bastards whichever way you looked at them. He was not making a joke. He offered it as a technical assessment, delivered flat. The nickname that followed him around the Caltech campus was the Lone Wolf, and he seemed to regard it as accurate rather than unkind. In 1933, he took Slipher's velocity data for the Coma cluster and fed it through the virial theorem. He was 35 years old. The result did not make sense. To hold the cluster together at the speeds observed, The mass required was roughly 400 times the mass he could account for by adding up every star in every galaxy in it. Not 4 times, not 40, 400. The visible cluster was, gravitationally speaking, a rounding error inside something much heavier that he could not see. He wrote that if this result held, it would lead to the shocking conclusion that far more matter was present than the luminous matter could explain. And in the German he wrote the paper in, he gave the missing component a name, Dunkel Materie, dark matter. And what? The paper appeared in Helvetica Physica Acta, a Swiss journal of modest circulation. It was published, catalogued, and then, for the better part of 40 years, left alone. It is worth being precise about why, because the reasons were not stupid. The first was the Hubble constant. The expansion rate of the universe is what converts a galaxy's redshift into a distance, and in 1933, the accepted value was wrong by roughly a factor of 7. That error placed the Coma cluster far further away than it actually is, which inflated every calculated size and therefore every calculated mass. Zwicky's factor of 400 was, in part, an artifact of a bad distance scale. The modern figure is far lower. The second was the data itself. There were only a handful of velocity measurements, and each one carried real uncertainty, a conclusion this radical resting on so few points invited caution. The third was the assumption underneath the whole method. The virial theorem only applies to a system in equilibrium, a system that is genuinely bound and has settled down. If the Coma galaxies were not truly gravitationally bound to each other, if they were a chance alignment, a temporary crowd of unrelated objects drifting past one another on the sky, then the theorem simply did not apply, and the missing mass was an illusion of perspective. Several astronomers argued exactly this. Every one of those objections was legitimate. What they lacked was anyone willing to systematically test them. And here is where the human problem meets the scientific one. A result does not spread by itself. It requires people who will explain it to others, defend it in seminars, connect it to adjacent results, and keep raising it until the field is forced to deal with it. A discovery needs advocates the way a river needs a channel. Zwicky had spent his professional life ensuring he had none. He would stand up at conferences and inform the room that his colleagues were wasting their careers on trivia while he alone pursued the real structure of the cosmos. He was correct about the importance of his problem. He was wrong about how a field changes its mind. So he published and moved on and assumed the evidence would do the work. He did not stop thinking about it, though. In 1937, 4 years later, he published a second idea that would matter enormously and would take even longer to arrive. He pointed out that a galaxy cluster, being an enormous concentration of mass, should bend the light of anything behind it. Einstein's general relativity required this. A cluster could act as a lens, distorting or even duplicating the images of more distant galaxies lying beyond it. And crucially, this is the part that shows how far ahead he was. The amount of distortion would depend only on the cluster's total mass. Regardless of whether that mass gave off light, it would be a second scale, completely independent of the virial theorem. No assumptions about equilibrium, no reliance on velocities at all. No telescope on Earth in 1937 could detect the effect. The first gravitational lens would not be found until 1979, 5 years after Zwicky's death. In the same period, he also began cataloguing. Between 1961 and 1968, he compiled a 6-volume catalogue of galaxies and clusters of galaxies, an enormous survey of tens of thousands of objects, assembled largely by himself. Astronomers still use it. Objects in it still carry his initial. It was, in a way, the most characteristic project he could possibly have chosen. Vast, meticulous, permanently useful, and completed almost entirely without collaborators. Meanwhile, the missing mass would not stay buried. As distance measurements improved through the 50s and 60s, the Coma velocities were remeasured, confirmed, and refined. The factor of 400 came down substantially. It did not go away. With better data, the stars in the cluster turned out to account for something like 1 or 2% of the mass needed to hold it together. Then, in the 1970s, orbiting X-ray telescopes changed the accounting. The satellite Uhuru, launched from a platform off the coast of Kenya in 1970, found that the space between the galaxies in a cluster is not empty. It is filled with gas extraordinarily thin, but heated to tens of millions of degrees by falling into the cluster's gravitational well and glowing in X-rays across the whole volume. In Coma, that gas turned out to be several times more massive than all the stars in all the galaxies combined. This was a genuine discovery of hidden ordinary matter. Most of the normal matter in a cluster is not in the galaxies at all. It is in that hot, diffuse gas between them, and it was not enough. Add every star, add every atom of the intracluster gas, and the total still falls short by a factor of something like 5 or 6 of what the motions require. The gas closed part of the gap. The rest of the gap stayed open, and it has stayed open ever since. The same test was run on every rich cluster anyone could reach: Perseus, Virgo, Centaurus. Each one a scale, each one returning the same verdict. The mass is present, the light is not. Zwicky died in 1974, at 75, in Pasadena. By then, the ground had begun to shift beneath the problem he had opened. Rotation curves for individual galaxies were appearing in the literature. Radio astronomers were pushing measurements far beyond the visible edges of galactic disks. The missing mass was acquiring the one thing it had always lacked, which was not a better argument but a larger body of evidence, arriving from several directions at once, from people who had never met. He did not live to see any of it settle. What he had proved in the end was narrower than it sounds and stranger than it sounds. He had not proved that a new kind of particle exists. He had proved that 1,000 galaxies were being held in place by something with roughly 100 times the gravitational pull of everything visible inside them, and that whatever it was spread through a volume 20 million light-years across. But a cluster is an enormous, messy, complicated system. There are mergers in progress, gas flows, galaxies falling in for the first time, uncertainties in every direction. Any single cluster measurement can be argued with. What the problem needed was something smaller and cleaner. A single object, well understood, with a simple geometry, where the prediction was unambiguous and the measurement could be repeated dozens of times over. It needed a spinning galaxy, and an instrument sensitive enough to measure the speed of stars right out at the faint edge where the light gives up. That instrument would not exist for another 30 years, and when it was finally built and pointed at Andromeda, the astronomer using it had spent her entire career being told, in one way or another, that she did not belong at the telescope. Vera Rubin decided she wanted to be an astronomer when she was 10 years old, in a bedroom in Washington with a north-facing window. She watched the stars wheel past that window at night and found she could not stop watching. She built her first telescope out of a cardboard tube and a lens, with help from her father, who took her to meetings of the local amateur astronomers club. She drew star maps on paper and taped them to the wall. When she applied to Princeton for graduate study in astronomy, the university did not send her the application materials. Women were not admitted to the graduate astronomy program and would not be until 1975. The reply she received informed her that the graduate catalogue was not available to women and suggested she look elsewhere. She kept that letter. She went to Cornell for her master's degree instead, where she happened to take courses from Philip Morrison and Richard Feynman, and then to Georgetown for her doctorate, which she completed while raising 4 children driving to evening classes, with her husband waiting in the car outside because she had not yet learned to drive at night. All 4 of those children would go on to earn doctorates in the sciences. Her early work had already brushed against the problem that would define her. In her master's thesis, presented at a meeting of the American Astronomical Society in 1950, she argued that galaxies might not be simply riding outward on the general expansion of the universe, but might also show large-scale collective motions, whole regions of the sky drifting in coordinated ways, which would imply concentrations of unseen mass pulling them. The reception was cold. The idea was not merely rejected, it was treated as not quite respectable. Rubin was 22, and a woman, and proposing a correction to the standard picture of cosmic expansion. The community was not interested. She learned something from that reception that shaped the rest of her career. She decided to work in areas where nobody was fighting, on measurements careful enough that the data would not need defending. She would go and simply measure things. What eventually made the crucial measurement possible was not a theory, it was a piece of hardware. In the late 1960s, an instrument builder named Kent Ford, working at the Carnegie Institution's Department of Terrestrial Magnetism in Washington, developed an image tube spectrograph. The problem it solved is straightforward to state. To measure how fast the outer parts of a galaxy are rotating, You need a spectrum from those outer parts, and out there, the starlight has thinned almost to nothing. On a conventional photographic plate, the exposure required to build up a usable spectrum from a galaxy's faint edge could run to many hours across multiple nights, and even then the signal sat buried in the grain of the emulsion. Ford's device intercepted the light before it reached the plate. Incoming photons struck a photocathode and were converted into electrons. Those electrons were accelerated and multiplied, and the amplified result was then recorded. The gain was enormous. Exposures that had required a full night could now be made in an hour or two, and regions of a galaxy that had simply been unreachable became routine targets. It was, at that moment, the most sensitive instrument of its kind in the world, and Rubin and Ford had it. There is a detail about the observing runs of this period that is worth keeping. In 1965, Rubin became the first woman granted observing time at the Palomar Observatory in California, home of the 200-inch Hale telescope, then the largest in the world. The observatory had no women's bathroom because the question had never come up. Rubin cut a skirt shape out of paper, taped it to the stick figure on one of the doors, and went back to work. She and Ford began a systematic survey of spiral galaxies, starting with Andromeda. It was the obvious first target, the nearest large spiral. Bright, well mapped, close enough that its individual regions could be resolved and measured separately. The prediction they were testing was simple, and everyone agreed on it. A spiral galaxy is, in its basic architecture, like a solar system. There is a central concentration of mass, a bright bulge of old stars, and a flattened disk of material orbiting around it. In our own solar system, the Sun holds essentially all the mass, and the consequence is a clean, well-known pattern. The further out you go, the slower things move. Mercury tears around the Sun at 48 kilometers per second. Earth moves at 30. Jupiter, 5 times further out than we are, ambles along at 13. Neptune crawls at 5.5. This is Kepler's third law, and it is not a curiosity. It is a direct consequence of gravity weakening with distance. Anything orbiting further from the mass needs less speed to stay in a stable path, and if it moved faster, it would climb away. So if you plot orbital speed against distance from the center, a graph astronomers call a rotation curve, a solar system produces a curve that rises steeply near the center and then falls away smoothly toward the edge. A spiral galaxy should do the same. The light is concentrated in the middle. The mass, everyone assumed, is where the light is. So the stars at the faint outer margins of the disk should be moving considerably slower than the stars near the bulge, in exactly the way Neptune moves slower than Venus. In 1970, Rubin and Ford pointed the spectrograph at the outer regions of Andromeda and measured the Doppler shift of absorption lines in the light of stars there, position by position along the disk. The curve did not fall, it went flat. At the furthest point they could reach, the stars were moving just as fast as stars much closer in. The velocity stopped declining and simply held, a level line running out into the last measurable light of the galaxy. Rubin's first assumption was that something was wrong with the measurement. That is the correct first assumption. She and Ford went looking for errors, checked the calibration, and then did the only thing that really settles the question, which is to go and measure more galaxies. They measured spirals of different types, bright ones and faint ones, massive ones and small ones. Galaxies tilted at every angle to our line of sight, because inclination affects how much of the true rotation shows up as a Doppler shift, and getting it wrong would produce systematic errors. By the mid-1970s they had dozens. Every single one was flat. Some were not merely flat. In some galaxies the curve continued rising gently outward. In the region where the visible light had already faded away, meaning the enclosed mass was still increasing at radii, where there was essentially nothing left to see. They were not the first to catch a glimpse of this. In 1939, Horace Babcock, working at the Lick Observatory in California, had measured a rotation curve for Andromeda as part of his doctoral thesis, and found the outer regions moving faster than they should. His data were thin, a handful of points, at the limit of what his instrument could do, and he was careful about it. He suggested the mass distribution might not be what astronomers assumed, or alternatively that something was distorting the absorption lines. Then the war came, and Babcock moved into other work, eventually becoming director of the Mount Wilson and Palomar observatories. His anomaly sat in the literature for 30 years, correct and unclaimed. There is a version of this story where that is a tragedy, and a truer version where it is simply how observation works. A single set of noisy points at the edge of an instrument's ability is not a discovery. It is a hint. What Rubin and Ford had was not a hint. It was a pattern, dense, repeatable, and taken with an instrument good enough that the outer points were as solid as the inner ones. And at the same time, from a completely different part of the spectrum, the same answer was arriving. Neutral hydrogen gas emits radiation at a wavelength of 21 centimeters. It is a faint emission. An individual hydrogen atom will produce it roughly once every 10 million years, but there is so much hydrogen in a galaxy that the signal is easily detectable with a radio telescope. And critically, the hydrogen extends much further out than the stars do. In many spirals, the gas disk reaches 2 or 3 times the radius of the visible starlight. That means radio astronomers could measure rotation in a region where optical astronomers had literally nothing to work with. Same Doppler principle, same physics, vastly greater reach. In 1978, a Dutch astronomer named Albert Bosma submitted a doctoral thesis at Groningen based on observations with the Westerbork synthesis radio telescope in the Netherlands. He had mapped the 21-centimeter emission across a sample of spiral galaxies, tracing their rotation far beyond the optical edge, out into regions where stars were effectively absent. The velocities did not fall. The flat line continued, into a region containing almost no visible matter at all. 2 independent techniques, 2 independent groups, 2 entirely different parts of the electromagnetic spectrum, agreeing. That is what ends an argument in astronomy. The implication is worth stating carefully, because it is the load-bearing inference of the entire subject. The orbital speed of an object at a given radius depends on the total mass enclosed inside that radius. That is a theorem, not an assumption for a roughly spherical mass distribution. Everything outside your orbit cancels out and contributes nothing, and everything inside pulls as though it were concentrated at the center. So if you measure the orbital speed at some distance from a galaxy's core, you have measured the mass inside that distance. Now, if the speed stays constant as you move outward, then the enclosed mass must keep growing, roughly in direct proportion to radius. Double the distance from the center, and you must have enclosed twice as much mass. But the light does not do that. The light runs out. Beyond the bright disk there is very little starlight and only thin gas, contributing almost nothing to the total. If the mass were where the light is, the enclosed mass would stop increasing and the curve would turn downward. It does not turn downward, so mass is being added at every step outward, in a region where there is nothing to see. And it is being added not in a disk would produce a different curve shape, but in a roughly spherical distribution surrounding the whole galaxy and extending far beyond it. That is a halo. It is not an interpretation. It is close to a direct reading of the graph. The numbers that came out of this were substantial. In the Milky Way, the rotation curve stays roughly flat at around 220 kilometers per second, out to at least 50,000 light-years from the center. And modern tracers, globular clusters, distant satellite galaxies, streams of stars torn from smaller galaxies falling in show the gravitational influence continuing far past that. The mass required to produce the curve is around 10 times the mass of all visible stars and gas inside the same radius. Counting the full halo, the ratio of total mass to visible light for a typical spiral runs to more than 100 times what the Sun's own mass and brightness would predict. Zwicky's cluster result had been reproduced in individual galaxies, one at a time, dozens of times over, by people who could go back and check. Rubin herself was consistently careful about what she was claiming. She would state the observation plainly that stars in a spiral are not moving the way Newton says they should, that they should be falling off, and that they are not, and she declined to speculate beyond it. She did not argue for a particular particle. She did not claim to know what the halo was made of. She reported what nature had shown her and left the explanation to whoever could find one. She kept observing well into her 80s, adding galaxies to the sample, mapping rotation, filling in the curve. She spent decades pushing, quietly and persistently, for women to be admitted to observing runs, to committees, to the National Academy of Sciences, which she joined in 1981. When she was invited to join the Pontifical Academy of Sciences, She used the occasion to press the point directly with anyone who would listen. She died in December of 2016, at 88. She never received the Nobel Prize. In 2019, the largest and most ambitious sky survey ever attempted, then under construction on a mountain in Chile, was renamed the Vera Rubin Observatory. It will photograph the entire visible southern sky every few nights for a decade, and a substantial fraction of its scientific purpose is mapping the distribution of the thing she found. By the early 1980s, the dark halo had stopped being a hypothesis and become part of the standard description of what a galaxy is. But it was still, at that point, an inference from motion, a weight deduced from a graph. And there was a much stranger question sitting underneath it, one that had nothing to do with rotation curves at all. Nobody had yet asked what a spiral galaxy would actually do if the halo were removed. When two theorists at Princeton finally ran that calculation, the answer was not that the galaxy would slow down or spread out. The answer was that it would tear itself apart within a few 100 million years, and that every spiral in the sky should therefore have been destroyed long before anyone existed to photograph one. A spiral galaxy, left to itself, destroys itself. In 1973, two theorists at Princeton, Jeremiah Ostraker and James Peebles, asked what seemed like a housekeeping question. Take a thin, rotating disk of stars, the kind of structure every spiral galaxy appears to be. Give the stars sensible orbits. Add up the gravity of all of them acting on all the others, and let the system run forward in time. What does it do? They ran it as a numerical experiment on a computer, following the mutual gravitational pull of a few hundred simulated particles. By modern standards, that is a trivially small calculation. It was enough. The disk did not stay a disk. A cold, thin, rotating stellar disk turns out to be violently unstable. Any small irregularity, a region where stars happen to be a little more crowded than average, which will always exist because stars are not distributed with perfect smoothness, does not stay small. It grows. Gravity pulls more stars into the crowded region, which makes it more crowded, which pulls in more stars. The irregularity organizes itself into a bar, a long, straight, rotating spine of stars running through the center of the galaxy. The bar then buckles out of the plane, twists, and funnels enormous quantities of material inward. Within a handful of rotation periods for a galaxy like ours, a few 100 million years, which is nothing, the elegant flat disk has become a swollen, disordered blob. The spiral arms are gone. The structure is gone. This should have happened everywhere. The pinwheels we photograph the arms of Andromeda, the two great sweeping arms of the Whirlpool Galaxy, the four arms of our own Milky Way should have collapsed into shapeless bulges billions of years ago, and yet roughly 2/3 of the large galaxies in the nearby universe are spirals, sitting there with their disks intact, some of them so thin that seen edge-on they look like a knife. Ostraker and Peebles found the resolution in the data that Rubin and the radio astronomers were producing at exactly that moment. Put the disk inside a massive, roughly spherical halo, something that carries a great deal of mass but does not itself lie in the plane, does not rotate coherently with the disk, and cannot participate in the instability and the behavior changes completely. The halo deepens the overall gravitational well without adding anything to the fragile rotating structure. It dominates the gravity at large radii, so a growing bar in the disk finds itself fighting against a background pull. It cannot reorganize. The instability is suppressed. The disk survives. The halo works, in effect, as an exoskeleton. It carries the load. The visible galaxy is the soft thing inside it. The paper they published carried a formal title about the numerical stability of flattened galaxies, but the question it actually asked was whether galaxies can exist without dark matter, and the answer it returned was no. This changed the standing of the halo. Before 1973, dark matter was an explanation for an observation, an odd rotation curve, a fast-moving cluster. After, it was a structural requirement. You could not build a spiral galaxy without one. The theoretical argument and the observational argument had arrived at the same object from opposite directions, which is the strongest kind of agreement science produces, because neither side was trying to accommodate the other. Then the sequence problem appeared, and it turned out to run deeper than stability. The halos did not form around galaxies. The galaxies formed inside halos that were already there. To see why, You have to go back to the first few 100,000 years after the Big Bang, when the universe was a hot, dense, opaque plasma. Everything was ionized. Protons and electrons moved freely, unbound, and photons could not travel any distance at all before scattering off a free electron. Light and matter were locked together in a single fluid. That coupling had a consequence. Radiation exerts pressure. So when a region of ordinary matter grew slightly denser than its surroundings and gravity began to pull it inward, the radiation trapped inside pushed back. The region did not collapse, it bounced. It compressed, rebounded, compressed again, a standing sound wave in the primordial fire, oscillating instead of gathering. Unquote. For as long as the universe stayed ionized, ordinary matter could not form structures, it could only ring. Dark matter had no such problem. It does not feel radiation pressure, because it does not interact with light. So while ordinary matter was oscillating helplessly, dark matter was already collapsing quietly, invisibly, gathering into clumps, growing denser, merging with neighboring clumps, and carving out a landscape of gravitational wells across the whole expanding universe. By the time the universe had cooled enough for protons and electrons to combine into neutral hydrogen, about 380,000 years in, and the radiation finally decoupled and streamed free, the terrain was already shaped. Ordinary gas, released at last from its coupling to light, did not have to start from scratch. It fell into wells that dark matter had spent hundreds of thousands of years excavating. The gas pooled at the bottom of those wells, and here its ability to radiate away heat, the property dark matter lacks, became decisive. It cooled. It compressed further. It flattened into disks, and at the densest points it collapsed into the first stars. So the order of events is not the intuitive one. The first structures in the universe were not stars and were not galaxies. They were halos, invisible, roughly spherical concentrations of unidentified material, growing and merging in the dark long before there was any light in the universe, other than the fading afterglow of its beginning. The galaxies came afterward, and they lit up at the bottoms of wells they had not dug. Everything visible is a tenant. The architecture came first, and it is still not identified. This is not a speculative picture. It is the standard model of cosmology, and it was built out of an enormous body of computational work that began in the 1980s and continues at increasing scale today. The technique is the numerical experiment Oestreicher and Peebles used, scaled up beyond recognition. You take the smooth, nearly featureless early universe revealed by the cosmic microwave background, a distribution with density variations of only a few parts in 100,000, and you fill a simulated volume with particles representing dark matter. Then you let gravity run. Every particle pulls on every other particle. The universe expands around them. You integrate forward for 13.8 billion years, and look at what you have. Early simulations followed a few thousand particles. By the 1990s, teams led by people including Simon White, Carlos Frenk, and Julio Navarro were running millions. The Millennium Simulation, in 2005, followed more than 10 billion particles through a cube of simulated space more than 2 billion light-years on a side. Current simulations run into the trillions of particles and include the messy physics of gas, star formation, and exploding stars alongside the gravity. Two results came out of that work that matter enormously. The first concerns the internal shape of a halo. Dark matter halos are not uniform balls. Their density rises steadily toward the center and falls off steeply at the outskirts, following a specific mathematical profile that Navarro, Frenk, and White described in a paper in 1996. Near the center, density runs roughly as 1 over the distance from the center. Far out, it falls as 1 over the distance cubed. In between, there is a smooth transition. What makes this remarkable is that it appears to be universal. Halos of wildly different masses, from the halo of a dwarf galaxy containing a few million suns worth of material to the halo of a giant cluster containing 1,000 trillion, adopt the same profile shape, differing only in scale. It was not predicted from first principles. It emerged from the simulations over and over, and nobody has ever fully explained why gravity acting on collisionless particles should always produce that particular curve. The second result concerns the largest scale of all. Dark matter does not distribute itself evenly through the universe, And it does not gather into isolated blobs either. It forms a network. Long filaments of material, thousands of times longer than they are thick, stretching for hundreds of millions of light years, joining at dense nodes where the largest clusters assemble. Between the filaments are sheets and walls. Between those are voids, enormous regions, sometimes 300 million light-years across, containing almost nothing at all. This is the cosmic web, and when galaxy redshift surveys began mapping the real universe in 3 dimensions, the Center for Astrophysics survey in the 1980s, then the 2-degree field survey and the Sloan Digital Sky survey, the map that came back looked like the simulations. Filaments, nodes, voids, the same structure, at the same scales, in the same proportion. That agreement is one of the strongest pieces of evidence in the whole subject, and it is easy to underrate because it is not a single dramatic observation. A simulation that starts with the tiny fluctuations measured in the oldest light in the universe, applies nothing but gravity acting on cold, collisionless matter, and runs forward for 13 billion years, produces a map of the universe that matches the one we actually live in. If dark matter were not there, or were not cold, or were not collisionless, that agreement would break. Our own position in that web is unremarkable and worth stating plainly. The Milky Way sits on a filament, not at a node. We are part of a small collection of galaxies called the local groupus, Andromeda, the Triangulum galaxy, and several dozen dwarfs which sits on the outskirts of the Virgo cluster's gravitational influence. The whole local group appears to be sliding toward a concentration of mass in the direction of the constellations Centaurus and Hydra at around 600 kilometers per second. The Milky Way's own halo weighs somewhere in the region of 1 trillion times the mass of the Sun and extends to a boundary, the radius inside, which material has settled into equilibrium of roughly 300,000 parsecs, just under 1 million light-years. That number deserves a moment. The visible Milky Way, the part in every photograph, the part with all the stars in it, is 100,000 light-years across. The halo is 10 times wider, which means the object you have been calling a galaxy your whole life is a bright ornament sitting in the middle of something 1,000 times larger by volume, and the ornament contains under 1/10 of the mass. And the halo does not end. That is the last thing worth saying about it. There is no edge, no surface, no boundary where the halo stops. The density simply declines with distance, gradually, and at some point out in the dark between here and Andromeda, it becomes indistinguishable from the general dark matter of the local group. The idea that a galaxy is a distinct object with a shape and a size is a convention inherited from looking at pictures. In mass, there is no such thing as an edge. There is only a fading. Weighing our own galaxy is, oddly, harder than weighing a distant one. From inside, we cannot see the whole thing at once, and every measurement is complicated by our position within the disk. The technique that has worked best in the last 2 decades uses stellar streams. When a small satellite galaxy or a globular cluster falls into the Milky Way, tidal forces pull it apart. The stars are not scattered randomly. They are drawn out into a long, thin ribbon that traces the orbit of the object that produced it, sometimes wrapping most of the way around the sky. The Sagittarius stream, produced by a dwarf galaxy currently being disassembled on the far side of the galactic center, wraps the entire sky at least twice. The stream called Palomar 5 is so thin and so cold, meaning its stars have very little random motion, that it is close to a perfect probe. A stream is essentially a chain of test particles on a known path, and because it follows an orbit, its shape encodes the gravitational field it has been moving through. Map the stream, and you can work backwards to the mass distribution that bent it. What made this practical was the European Space Agency's Gaia mission, which operated from 2013 until 2025. Gaia measured the positions, distances and motions of nearly 2 billion stars with a precision that, for the nearest ones, corresponds to seeing the width of a human hair from 1,000 kilometers away. It converted the Milky Way from a system we could photograph into a system we could actually measure. With Gaia data, the stream method and the escape velocity method converged. The second one is beautifully simple in principle. Measure the fastest stars in the solar neighborhood and reason that any star moving faster than the local escape velocity would have left long ago. The fastest stars still present therefore mark the boundary. That boundary, in our part of the galaxy, sits at somewhere around 550 kilometers per second. Both methods return a total mass for the Milky Way of roughly 1 trillion times the mass of the Sun, with the uncertainty still sitting at around a factor of 2, which tells you how difficult the measurement remains. The stars contribute perhaps 5% of that. The gas contributes a little more. Everything else, the great majority, is the halo. All of this, the rotation curves, the cluster velocities, the disk stability, the cosmic web, rests on one assumption that has been sitting quietly underneath every argument so far: that when we see something moving, we know what is pulling it. That Newton's law of gravity and Einstein's refinement of it apply unmodified at scales 100 million times larger than anything they were tested on. There is no obvious reason that assumption must be true. Every law in physics has a domain where it was verified, and gravity was verified in the solar system, on orbits a few light hours across, at accelerations enormously larger than those felt by a star drifting at the edge of a galaxy. There is a way to check. It requires weighing something without using motion at all, measuring mass through an entirely different physical effect, one that would still work even if the force law were wrong. Zwicky had described exactly such a method in 1937, and then waited the rest of his life for a telescope capable of using it. Light bends around mass. Einstein worked out the size of the effect in 1915 as one of the first consequences of general relativity. In his picture, gravity is not a force reaching across space and pulling on things. Gravity is the shape of space itself. A mass distorts the geometry around it, and everything moving through that region, including light, which has no mass at all, follows the straightest available path through a curved landscape. From outside, that looks like a deflection. The prediction was specific and testable. Starlight grazing the edge of the Sun should be deflected by about 1.75 arcseconds. An arcsecond is 1/3600th of a degree. 1.75 of them is roughly the angle a coin makes when viewed from 3 kilometers away. The test required a total solar eclipse, because otherwise the Sun's glare makes it impossible to see stars anywhere near it. In May of 1919, Arthur Eddington took an expedition to the island of Principe, off the coast of West Africa, while a second team went to Sobral in Brazil, and both photographed the star field around the eclipsed Sun, comparing those plates against photographs of the same stars taken months earlier. When the Sun was elsewhere in the sky, they measured the shift. The stars had moved by about the predicted amount. The result was announced in London that November, and Einstein became, essentially overnight, the most famous scientist alive. Zwicky saw the implication for astronomy that almost nobody else did. If a star can bend light measurably, a galaxy cluster carrying 1,000,000,000 times more mass will bend it enormously. And a cluster sitting between us and something further away would act as a lens, distorting the image of the background object, magnifying it, in extreme cases splitting it into multiple images of the same thing appearing in different places on the sky. The amount of distortion depends only on the total mass of the lens and how it is arranged, not on what the mass is made of, not on whether it emits light, not on whether anything inside the cluster is moving, or in equilibrium, or bound at all. That is what makes it valuable. Every method we have discussed so far measures mass by watching things move, which means every method so far depends on the law of gravity being what we think it is. Lensing depends on general relativity too, of course, but it tests a completely different aspect of it, and crucially, it can locate mass on the sky. It does not just tell you how much, it tells you where. The first gravitational lens was found in 1979, by accident. Dennis Walsh, Bob Carswell and Ray Wayman were following up radio sources in the constellation Ursa Major with a telescope in Arizona. One source turned out to be a quasar, the blazing core of a young galaxy, powered by matter falling into a supermassive black hole, so bright that it outshines its entire host galaxy and can be seen across most of the observable universe. This quasar appeared to have a twin, two point-like objects, separated by about 6 arcseconds on the sky. That would be unremarkable, except that when they took spectra of both, the spectra were identical, not similar, identical, the same emission lines, at the same wavelengths, indicating the same redshift, which is to say, the same distance. Two quasars of the same type at the same distance, 6 arcseconds apart, would be an outrageous coincidence. They were not two quasars. They were one quasar, seen twice, 20 Its light split into two paths by the gravity of a galaxy sitting between us, and it, a galaxy so faint against the quasar's glare that it took further observations to detect it at all. Einstein had considered this possibility as early as 1912 and had dismissed it as unobservable in practice. He was wrong about that, though it took 67 years to demonstrate it. The field expanded quickly from there. Astronomers began finding giant arcs, entire background galaxies smeared into long luminous crescents by the gravity of a foreground cluster, curved around the cluster's center like scratches on glass. They found Einstein rings, where the alignment of source, lens, and observer is so nearly perfect that the background object is smeared into a complete circle. Some of the deepest images ever taken the Hubble frontier fields, and now the images returned by the James Webb Space Telescope deliberately point at massive clusters and use them as natural telescopes, letting cluster gravity magnify galaxies from the first few 100 million years of the universe that would otherwise be far too faint to detect. But the technique that mattered most for dark matter was not the dramatic one. Strong lensing arcs, rings, multiple images requires near-perfect alignment and only occurs in the densest cores of the most massive clusters. It is rare, and it only probes the very center. Weak lensing works everywhere. The idea is that every mass concentration distorts the images of every background galaxy behind it, but usually by a tiny amount, an elongation of a few percent, far too small to notice in any individual galaxy, because galaxies come in all shapes, and there is no way to know what a particular one looked like before its light was bent. The trick is statistical. If you measure the shapes of tens of thousands of faint background galaxies in a patch of sky, their intrinsic orientations should be random and average out to nothing. Any residual alignment, any systematic tendency for them to be stretched in a coherent pattern around some point, is not intrinsic. It is the signature of mass along the line of sight. Measure the pattern of that coherent stretching across a field, and you can reconstruct the mass distribution that produced it, not just the total. A map, mass, pixel by pixel, projected onto the sky, derived from nothing but the shapes of distant galaxies and the geometry of general relativity. No velocities, no assumption of equilibrium, no requirement that the system be settled or bound or even stable. Weak lensing has since been scaled up enormously. Surveys covering thousands of square degrees, the Dark Energy Survey, the Kilo Degree Survey, the Hypersuprime-Cam Survey, and now the European Space Agency's Euclid mission, launched in 2023, specifically to map the geometry of the dark universe, to measure the shapes of hundreds of millions of galaxies, to build three-dimensional maps of where mass sits across cosmic time. But the single most decisive use of the technique was on one object, and the reason it was decisive is that the universe had already performed the experiment for us. It happened around 150 million years before the light we now see left the scene, which itself left roughly 3.4 billion years ago. Two galaxy clusters collided. The system is catalogued formally, but everyone calls it the bullet cluster, after the shape of its X-ray emission, a compact, blunt-nosed cone of hot gas driving forward with a shock front curved in front of it like the bow wave of a boat. A smaller cluster has passed clean through the core of a larger one, at a relative speed of around 4,500 kilometers per second. It is among the most energetic events in the observable universe. To see why this collision is a laboratory, you need to keep three components separate. First, the galaxies. Stars are extraordinarily small compared to the distances between them. If the Sun were the size of a grape, the nearest star would be another grape 1,000 kilometers away. When two galaxies pass through each other, the odds of any two stars actually colliding are effectively zero. Galaxies behave in a cluster collision, like collisionless particles. They pass through one another and keep going, barely slowed, like two swarms of insects flying through the same volume of air. Second, the hot gas. Most of the ordinary matter in a cluster is not in the galaxies at all. It is in that diffuse intra-cluster gas, heated to tens of millions of degrees, which outweighs all the stars combined by a factor of several. And gas is emphatically collisional. When two clouds of gas meet at thousands of kilometers per second, they slam into each other. Ram pressure strips the gas out of each cluster, decelerates it, compresses it, heats it further, and leaves it piled up in the middle, lagging behind the galaxies that were carrying it. Third, whatever accounts for the missing mass. Now the prediction splits cleanly, and this is the whole point. If dark matter is a real substance, collisionless, feeling only gravity, then it should behave like the galaxies. It should sail straight through the collision without slowing, and end up out ahead with them separated from the gas. If instead there is no dark matter, and the apparent extra mass is an artifact of gravity behaving differently than we think, then the mass must be tied to the ordinary matter that is actually there, and most of the ordinary matter is in the gas. So the gravitational mass should sit with the gas, in the middle, where the gas has piled up. Two possibilities, two different places on the sky, one measurement to distinguish them. In 2006, a team led by Douglas Clow, then at the University of Arizona, working with Maxim Markovich at the Harvard-Smithsonian Center for Astrophysics, put the two instruments together. The Chandra X-ray Observatory mapped where the hot gas was. The Hubble Space Telescope, along with ground-based imaging, provided the deep pictures of faint background galaxies needed for weak lensing, which mapped where the mass was. The mass was not with the gas. The reconstruction produced two clear mass concentrations, one for each of the two clusters, and both of them sat with the galaxies out ahead, having passed through the collision undisturbed. The X-ray gas, containing the overwhelming majority of the ordinary matter in the system, sat between them, stripped and slowed and glowing. The separation was around 100 kiloparsecs, roughly 300,000 light-years. That is not a subtle statistical preference buried in an analysis. It is a gap you can see in the image with your eyes. What that means in plain terms, in this system, most of the mass has become physically separated from most of the atoms. The gravity is over here, the ordinary matter is over there. They are in different places. That is very hard to explain by modifying the law of gravity, because a modified force law still has to be sourced by something. If the source is the visible matter, the extra gravity should follow the visible matter, and the visible matter is mostly gas, and the gas is in the middle. Instead, the gravity went where the collisionless component went. It is worth being accurate about how much this settles. The bullet cluster does not mathematically eliminate every possible alternative theory. Theorists have constructed variants, some involving massive neutrinos providing a collisionless component, some involving non-local modifications of gravity, where the field does not simply track the local matter that can be made to reproduce the offset. Nothing in physics is ever closed by a single image, but it moved the argument decisively, and it did so in a way that is easy to state and hard to argue around. Explaining a flat rotation curve with a modified force law is one thing. Explaining why the gravitational mass in a merging cluster has walked away from the atoms is quite another, and every attempt to do it requires adding assumptions rather than removing them. And it was not a one-off. Since 2006, the same measurement has been repeated on other merging systems. The system nicknamed the Baby Bullet, a smaller and more distant collision found 2 years later, shows the same offset. The Pandora Cluster, a chaotic pileup of at least 4 separate clusters colliding simultaneously, one of the most complicated gravitational scenes anyone has mapped, shows mass concentrations that do not track the gas. The Musket Ball Cluster, a slower and older collision, shows the same separation at a later stage. Each one is a natural experiment. In each one, the universe has done something we cannot do in a laboratory. Taken a system containing both visible and invisible components and physically pulled them apart at a scale of millions of light years, and left the results sitting on the sky for us to photograph. These collisions also put a limit on something else. If dark matter particles could scatter off one another even weakly, the dark matter clumps would have been slowed a little in passing through and would lag slightly behind the galaxies. Measuring how closely the mass peaks track the galaxies puts an upper bound on how strongly dark matter can interact with itself. The current limits are severe. Whatever it is very nearly perfectly collisionless, one more entry in a specification that has grown steadily more detailed, while the object it describes has remained entirely unidentified, because that is where this leaves us. Between the rotation curves, the cluster dynamics, the disk stability calculations, the structure of the cosmic web, and now a set of collisions in which the mass and the matter have been physically separated, the question of whether dark matter exists is, for most of the field, closed. The question is, what it is. And the sharpest constraint on that, the measurement that pins down not just how much there is, but what it cannot possibly be made of, did not come from any galaxy or cluster at all. It came from a persistent hiss in a radio antenna in New Jersey that 2 engineers spent a year trying to eliminate, including by evicting a pair of pigeons. In 1964, at Bell Laboratories in Holmdel, New Jersey, Arno Penzias and Robert Wilson were trying to get rid of a noise. The instrument was a horn antenna, a large aluminium funnel, about 6 meters across at the mouth, originally built to receive signals bounced off early communications satellites. Penzias and Wilson had it for radio astronomy, and radio astronomy at that level of precision requires knowing exactly how much noise your own equipment produces, so that you can subtract it and see what is actually coming from the sky. They could not account for all of it. There was a faint, steady hiss that would not go away. They cooled the receiver with liquid helium to a few degrees above absolute zero, which removes most thermal noise from the electronics. The hiss stayed. They checked every joint and connection in the system. They considered radio interference from New York City, 25 miles away, and pointed the horn at the city to measure it, and it was not that. They considered residual radiation from a high-altitude nuclear test conducted 2 years earlier, and the timing did not fit. They discovered that a pair of pigeons had been roosting inside the horn and had left deposits on the interior surface, which Penzias later described with careful restraint as a white dielectric substance. They removed the pigeons. They cleaned the horn. The pigeons came back. They dealt with the pigeons again. The hiss remained, exactly as before. It had 2 properties that made it strange. It was the same in every direction they pointed. No brighter toward the galactic center, no fainter toward empty sky, uniform across the whole celestial sphere. And it did not vary with the seasons, which ruled out anything in the solar system. Whatever it was, it filled the universe evenly, and it corresponded to a temperature of a little over 3 degrees above absolute zero. 50 kilometers away, at Princeton, a group led by Robert Dicke was building an antenna to look for precisely that. Dicke's group had worked through the theory. If the universe began in a hot, dense state and has been expanding ever since, then in the early period, it must have been an opaque plasma, filled with radiation in thermal equilibrium with matter. When it cooled enough for that plasma to become transparent, the radiation would have been released, and it would still be here, but stretched by the expansion of space, its wavelength lengthened by a factor of 1,000 or more, cooled from thousands of degrees down into the microwave band, a faint uniform glow, filling all of space at a few degrees above absolute zero. They were building the receiver to look for it. Jim Peebles, the same Peebles who would work out the disk instability problem with Ostraca 9 years later, had done much of the theoretical calculation. Penzias heard about the Princeton work through a chain of colleagues and telephoned Dicke. Dicke listened, hung up the phone, turned to the people in the room, and told them they had been scooped. The 2 groups published side by side in 1965. Penzias and Wilson described the measurement and made no claim about its meaning. Dicke's group published the interpretation. Penzias and Wilson received the Nobel Prize in 1978. The cosmic microwave background is the oldest light there is, and it will remain the oldest light there is, permanently. Nothing earlier can be seen, because before the moment that produced it, the universe was not transparent. Here is what happened. For the first 380,000 years, the universe was hot enough that atoms could not hold together. Every electron that tried to bind to a proton was immediately knocked free again by an energetic photon. So matter existed as a plasma of free charged particles, and free charged particles scatter light extremely efficiently. A photon could travel only a very short distance before running into an electron and being deflected in a random direction. The universe was not dark, it was blindingly bright and completely opaque, like being inside a fog lit from every side. Then expansion cooled it below roughly 3000 Kelvin, and the photons no longer had the energy to break atoms apart. Electrons combined with protons, neutral hydrogen formed, and neutral atoms, unlike free electrons, barely scatter light at all. The fog cleared everywhere in a period of a few tens of thousands of years. At that moment, the photons that had been bouncing endlessly between particles were suddenly free, and they have been traveling in straight lines ever since for 13.8 billion years. The expansion of space stretched their wavelengths along the way by a factor of about 1100, dropping them from the visible and infrared down into microwaves, and cooling the effective temperature from 3000 Kelvin to 2.725 Kelvin today. That is the hiss in the Holmdel antenna. It is the moment the universe became transparent, arriving from every direction at once, still going. And it is very nearly, but not quite, perfectly smooth. Embedded in it are temperature fluctuations, patches slightly hotter and slightly colder than the average, at a level of a few parts in 100,000. If the sky were an ocean, these would be ripples, a fraction of a millimeter high. Those ripples are not noise. They are a photograph of the density variations in the universe at the instant it became transparent, and they are the seeds from which every structure that now exists eventually grew. More than that, they have a specific pattern, and the pattern is acoustic. In the plasma before decoupling, gravity and radiation pressure were in opposition. A region that started slightly denser pulled in more material through gravity. As it compressed, the trapped radiation pushed back harder. The region rebounded, overshot, became underdense, and gravity pulled it back again. Compression, rarefaction, compression, a sound wave, propagating through the primordial plasma at a substantial fraction of the speed of light. The universe rang. Not metaphorically. There were genuine pressure waves in a genuine fluid, and they behaved the way sound behaves in any medium, with the crucial difference that this medium filled all of space, and the note lasted for hundreds of thousands of years. And then, at decoupling, the pressure vanished. Photons streamed away, the fluid ceased to be a fluid, and the wave pattern froze exactly as it was at that instant, printed permanently onto the radiation released. Which means the temperature map of the microwave sky is a record of a standing wave pattern in the early universe, and like any standing wave, it carries information about the medium that produced it. Just as the sound of a struck bell tells you about the bell's size, thickness and material, the pattern of ripples in the microwave background tells you about the composition of the universe that rang. Reading it took 3 generations of instruments. The Cosmic Background Explorer satellite, launched in 1989, did 2 things. It measured the spectrum of the background radiation and found it to be the most perfect blackbody spectrum ever measured, matching the theoretical curve of pure thermal radiation, so exactly that the error bars are smaller than the thickness of the line on the published graph. That single measurement essentially eliminated every alternative explanation for the origin of the radiation, and it detected, for the first time, the temperature fluctuations at the level of a few parts in 100,000, exactly where theory required them. John Mather led the spectrum work, George Smoot led the fluctuation measurement, and they shared the Nobel Prize in 2006. But that satellite's resolution was about 7 degrees on the sky, 14 times the width of the full moon. It could see that the ripples existed. It could not resolve their structure. The Wilkinson Microwave Anisotropy Probe, launched in 2001, improved that to about 1/5 of a degree and mapped the entire sky. Its first major data release, in 2003, is the point at which cosmology became a precision science. Before it, the basic parameters of the universe were known to within factors of 2. After it, several were known to within a few percent. Then the European Space Agency's Planck satellite, launched in 2009, pushed the resolution to about 5 arc-minutes and added precise measurements of the polarization of the radiation as well as its temperature. Its final data release in 2018 gives the numbers that define the modern picture. Here is how those maps become a measurement of dark matter. You take the temperature map and ask a statistical question. How much fluctuation is there at each angular scale? How much power is there in patches 1 degree across versus patches 1/2 a degree across versus 1/10 of a degree? The answer is a curve, and called the power spectrum, and it is not featureless. It has a series of distinct peaks. The peaks exist because of the ringing. Regions of a particular size had exactly enough time between the beginning of the universe and decoupling to complete one full compression. Those show the largest temperature contrast and produce the first and largest peak. Smaller regions oscillate faster and had time to compress, rebound and compress again, producing the second peak, and so on down the scale. Each peak carries different information. The position of the first peak measures the geometry of the universe. The physical size of those first peak regions at decoupling is calculable from known physics. Their apparent angular size on our sky depends on whether light has travelled to us through flat space or curved space. Measure the angle, compare it to the known size, and you have the curvature of the universe directly. The answer, from the probe and confirmed by Planck, flat, to within a fraction of a percent. The height of the second peak relative to the first measures the density of ordinary matter protons and neutrons. Ordinary matter adds inertia to the oscillating fluid. Loading a spring with more mass makes compression deeper and rebound weaker, so the odd-numbered peaks, which correspond to compressions, are boosted relative to the even-numbered peaks, which correspond to rarefactions. The ratio between them is a direct measurement of how much ordinary matter was present, and the third peak is the one that dark matter controls. Dark matter does not oscillate. It does not feel the radiation pressure. So while the ordinary plasma is ringing, dark matter is just sitting in the gravitational wells, deepening them, and it does not get pushed back out on the rebound. The effect of that is to sustain the oscillations against the damping that would otherwise reduce them at smaller scales, and it raises the third peak relative to the second by an amount that depends directly on how much non-oscillating mass was present. Measure the height of the third peak, and you have weighed the dark matter in the universe at an age of 380,000 years. The numbers that come out of this, from Planck's final release, are the ones that define the standard model of cosmology. By total mass and energy content, the universe is roughly 4.9% ordinary matter, 26.8% dark matter, and 68.3% dark energy, a separate problem entirely, and one for another night. Restrict attention to matter alone, and the split is about 15% ordinary, 85% dark, which is the number this whole story began with. Now, the part that closes the door. There is a completely independent way to measure the amount of ordinary matter in the universe, and it comes from the first 3 minutes rather than the first 380,000 years. In that opening window, the universe was hot and dense enough for nuclear fusion to occur everywhere at once. Protons and neutrons fused into deuterium, then helium, with traces of lithium. Then expansion cooled things below the threshold and the process shut off permanently, leaving behind a fixed mixture of light elements that has been the raw material of everything since. The proportions in that mixture depend sensitively on one thing: the density of protons and neutrons at the time. Deuterium is especially sensitive because it is fragile in a denser universe. More of it gets processed onward into helium, leaving less behind. So, astronomers measure the deuterium abundance in pristine gas clouds, ones that have never been inside a star, seen in absorption against distant quasars. That measurement gives the density of ordinary matter in the early universe, and it agrees precisely with the ordinary matter density derived from the second peak of the microwave background. Two completely different physical processes, separated by 380,000 years, measured with completely different instruments, returning the same number, which means the ordinary matter budget is nailed down twice over, and it is far too small. The total matter density from the third peak is more than 5 times larger than the ordinary matter density from the second peak and from the deuterium. Dark matter is not made of protons and neutrons. It is not faint stars, not cold gas, not rocks, not dust, not failed stars, not black holes formed from collapsed stars. Anything made of ordinary atoms would have participated in that early fusion and shown up in the deuterium. It is something else, something not in the catalogue. The precision here deserves to be stated plainly, because it is what makes the situation so peculiar. Cosmologists know the density of dark matter in the universe to within about 1%. They know it is cold, meaning it was moving slowly compared to light when structure began forming, because if it had been fast, it would have streamed out of small density fluctuations and erased them, and the small-scale structure we observe would not exist. They know it is very nearly collisionless, from the cluster collisions. They know it does not interact with light at any level we can detect, in any part of the spectrum, or it would have shown up in the microwave background's polarization. They know it was already present in the first minutes of the universe, because its gravity shaped the acoustic oscillations. They know it is stable over at least 13.8 billion years, because it is still here. That is a specification. Cold, collisionless, non-baryonic, electrically neutral, stable across the age of the universe, present in the right abundance from the beginning, interacting with ordinary matter, if at all, only very weakly. It is a detailed and demanding description of something nobody has ever detected. And for 40 years, one candidate fitted that description so neatly and for such elegant theoretical reasons that a generation of physicists built their careers around finding it in laboratories buried under mountains, in tanks of liquid xenon cooled to 175 degrees below zero, shielded by kilometers of rock, made from copper recovered from sunken ships and lead salvaged from Roman shipwrecks because ordinary metal was too radioactive to use. They built the quietest places on Earth, and then they waited. The candidate is called the weakly interacting massive particle, and physicists shortened that to WIMP, which tells you something about the mood of the field in the 1980s. The name is not a theory, it is a job description. A WIMP is any particle heavy enough to be non-relativistic in the early universe, somewhere between a few times and a few thousand times the mass of a proton, that is electrically neutral, stable, and interacts with ordinary matter only through gravity, and something of roughly the strength of the weak nuclear force. The weak force is the one responsible for certain kinds of radioactive decay. It is called weak because it is. At everyday energies, it is something like 10,000 million times feebler than electromagnetism. Interactions mediated by it are rare. Neutrinos, which feel only the weak force and gravity, pass through the entire Earth in enormous numbers without noticing it. So a WIMP would be, in effect, a heavy neutrino-like object, invisible, passing through everything, present in vast numbers. What made this candidate compelling was not that it fit the requirements. Many things could be invented to fit the requirements. What made it compelling was that nobody had to invent it. By the 1970s and 80s, particle physicists had their own reasons entirely unrelated to astronomy to suspect that new particles existed at a particular energy scale. The standard model of particle physics, which describes every particle ever detected, has a structural awkwardness in it involving the mass of the Higgs boson. The most popular proposed solution was supersymmetry, the idea that every known particle has a heavier partner not yet discovered. And in most versions of supersymmetry, the lightest of those partners is stable, electrically neutral, and interacts only weakly. That is a dark matter candidate, arriving unbidden from a theory built to solve a completely different problem. And then there is the coincidence that gave the field its confidence, sometimes called the WIMP miracle. In the hot early universe, such particles would have been produced and destroyed constantly, in equilibrium with everything else. As the universe expanded and cooled, production would have stopped, and the particles would have continued annihilating with each other until the density dropped low enough that they could no longer find each other, at which point the remaining population would be frozen in permanently. Physicists call this freeze-out, and the leftover population is called a thermal relic. You can calculate how many survive. It depends on the interaction strength. Stronger interaction means they keep annihilating longer and fewer survive. Weaker interaction means they stop finding each other earlier and more survive. Run that calculation with an interaction strength characteristic of the weak nuclear force and a mass around 100 billion electron volts, which is to say, precisely the values suggested by particle physics for entirely independent reasons, and the leftover abundance comes out at approximately the observed density of dark matter. Not within a factor of 1,000, within a factor of a few. That is the miracle. Two completely unrelated fields, cosmology and particle physics, pointing at the same mass scale and the same interaction strength from opposite directions. It was too neat to ignore, and for 30 years it drove one of the largest experimental programs in the history of physics. Because if WIMPs interact weakly rather than not at all, then, very occasionally, extremely occasionally, one of the million or so passing through your body every second should strike an atomic nucleus and bounce off it. That recoiling nucleus would carry away a tiny amount of energy in the region of a few thousand electron volts. Enough, in the right material, to produce a flash of light, a small cloud of liberated electrons, or a measurable rise in temperature. The entire problem is that everything else also produces those signals, constantly. Cosmic rays strike the atmosphere and produce showers of particles that rain down at ground level continuously. Natural radioactivity in rock, in soil, in concrete, in air, produces gamma rays and beta particles. The materials the detector itself is built from contain trace radioactive isotopes. Even the human body is radioactive, mostly from potassium. Against that background, a signal expected at a rate of perhaps a handful of events per ton of target per year is invisible. So the experiments went underground, and then they went further than that. They became an exercise in the construction of silence. The Gran Sasso National Laboratory sits beneath the Apennine Mountains in central Italy, reached through a side passage from a motorway tunnel. There are 1,400 meters of rock overhead, which reduces the cosmic ray flux by a factor of about 1 million. Inside are enormous halls containing steel vessels, clean rooms, and cryogenic plants. It is the largest underground laboratory in the world. There are others. The Sanford Underground Research Facility occupies the former Homestake Gold Mine in South Dakota. At a depth of nearly 1.5 kilometers, the same mine where Raymond Davis ran the experiment that first detected solar neutrinos and discovered they were arriving in the wrong numbers. SNOLAB is 2 kilometers down in an active nickel mine near Sudbury. Ontario, where researchers descend in the same cage as the miners and then shower and change into clean room clothing before entering the laboratory. The Kamioka Observatory in Japan sits under a mountain in a converted mine. The China Jingping Underground Laboratory, beneath a mountain in Sichuan, has the deepest rock overburden of any laboratory on Earth at around 2,400 meters. Depth handles the cosmic rays. The rock itself is still radioactive, so the detectors are surrounded by shielding, layers of purified water or liquid scintillator, or ultra-pure copper or lead. And the lead is where this gets strange, in a way that is hard to forget. Freshly smelted lead contains a radioactive isotope, lead-210, with a half-life of about 22 years. For the most sensitive experiments, even that faint activity is too much. What is needed is lead that has been sitting undisturbed long enough for the isotope to decay away, and shielded during that time from cosmic rays that would regenerate it. Lead recovered from ancient shipwrecks meets that requirement. Roman lead ingots that have spent 2,000 years on the seabed under 100 meters of water are among the least radioactive metal available anywhere. Several experiments have used them. There has been genuine and reasonable argument between physicists and archaeologists about the practice. Copper presents a similar problem, solved differently. Copper for detector components is electroformed underground, grown atom by atom out of solution in a laboratory already shielded by rock, so that it is never exposed to cosmic rays at all after production. The material of choice for the largest detectors is liquid xenon. Xenon is a noble gas, chemically inert, which becomes a liquid at around 108 Kelvin. It is dense, and a heavy nucleus makes a bigger target. It has no long-lived radioactive isotopes of its own, and it can be purified to an extraordinary degree, because most contaminants freeze out or can be chemically removed, while the xenon itself remains untouched. The detector design is elegant enough to be worth describing. A large tank is filled with liquid xenon, with a thin layer of xenon gas above it. Arrays of extremely sensitive light detectors watch from above and below. A strong electric field runs vertically through the liquid. If a particle strikes a xenon nucleus, two things happen. First, the recoil produces an immediate flash of ultraviolet light, the primary scintillation signal. Second, it knocks some electrons free from xenon atoms. The electric field drags those electrons upward through the liquid, where they are pulled into the gas layer and produce a second, larger flash. From those two signals you get everything you need. The time delay between them tells you the depth at which the interaction occurred, because the electrons drift at a known speed. The pattern of light across the detector array gives you the horizontal position, so every event is located in 3 dimensions inside the tank. That matters enormously. Background radiation comes from outside, so it interacts predominantly near the edges. The innermost core of the tank, the fiducial volume, is shielded by the xenon around it, which is itself an excellent absorber. Events in the quiet core are far more likely to be genuine, and the ratio of the two signals distinguishes what was hit. A particle striking a nucleus produces a different ratio than a particle striking an electron. Since almost all background comes from gamma rays and beta particles which interact with electrons, this provides a powerful discrimination. The result is a detector that can identify a single nuclear recoil, deposit a few thousand electron volts of energy, and reject essentially everything else. The Xenon collaboration at Gran Sasso built these in a sequence: 10 kilograms of xenon, then 100, then more than 3 tons. For the experiment that ran from 2016 to 2018, then nearly 6 tons for the current generation, which began taking data in 2021. The Lux Zeppelin experiment in South Dakota uses 7 tons and reported its first results in 2022. The Panda X experiment in China operates at a comparable scale. Others use different technologies entirely. Germanium and silicon crystals cooled to a few thousandths of a degree, above absolute zero, where a single nuclear recoil produces a measurable temperature rise and a detectable pulse of vibration through the crystal lattice. Between them, they represent decades of work, hundreds of physicists, and hundreds of millions of dollars. They have found nothing. Not nothing in the sense of an ambiguous result, nothing in the sense that the number of events observed matches to within statistical error, the number expected from known backgrounds, with no excess of any kind. What that produces is not a discovery but a boundary. Each null result sets an upper limit on how strongly a WIMP of a given mass can interact with a nucleus, because a stronger interaction would have produced events that were not seen. Those limits are now extraordinary. For a particle around 30 times the mass of a proton, the interaction cross-section, effectively the target area a nucleus presents to a passing WIMP, is now constrained to below 10 to the power of minus 47 square centimeters. To put that number somewhere, the physical cross-sectional area of a proton is around 10 to the power of minus 26 square centimeters. The limit is 21 orders of magnitude smaller, a billion times smaller than the particle itself. At that interaction strength, a WIMP could pass through the entire Earth, through the mountain, through the detector, and through the far side of the planet, and the odds of it disturbing a single nucleus anywhere along the way are negligible. Over roughly 30 years, the sensitivity of these experiments has improved by a factor of around 100 million. The parameter space favored by the simplest supersymmetric models has been almost entirely covered. The models that made the WIMP miracle so compelling in the first place are now, in their most natural forms, largely excluded. There is one experiment that says otherwise, and it has been saying so for more than 20 years. The Dharma experiment, also at Gran Sasso, uses crystals of sodium iodide rather than liquid xenon and looks for something different. Rather than trying to identify individual dark matter events, it looks for the annual modulation, the seasonal rise and fall in the rate of events that should occur as the Earth's orbital motion adds to and subtracts from the Sun's motion through the halo, and it sees one. A sinusoidal variation in the low-energy event rate, peaking around the start of June and bottoming around the start of December, with an amplitude of about 1%, sustained across more than 2 decades of continuous operation and multiple detector upgrades. The statistical significance is far above the conventional threshold for a discovery. The dates match the astronomical prediction. The amplitude is in the right region. The phase has been stable for 20 years. People, and nobody else can find it. The xenon detectors have excluded the parameter space that Dharma's signal would require by several orders of magnitude, not marginally, but overwhelmingly, under any standard assumption about how dark matter interacts. And experiments built specifically to test Dharma using the same sodium iodide technology in order to remove any argument about target materials have not confirmed it. The Cosine experiment in South Korea, operating in a tunnel under a mountain, and the Anais experiment beneath the Pyrenees in Spain have both now accumulated years of data. Neither sees the modulation. The most likely explanation is that the modulation is real but is not dark matter, that some background varies seasonally in a way that has not been modelled. Temperature, humidity, the muon flux through the mountain, which does vary annually as the atmosphere above expands and contracts with the seasons. Radon concentration in the laboratory air, which varies with ventilation patterns. The Dharma collaboration disputes all of these and has not released its raw data in a form allowing independent reanalysis. The relationship between that group and the rest of the field has been strained for a long time and shows no sign of resolving. It is an uncomfortable situation and worth sitting with, because it is what a genuine, unresolved disagreement in physics actually looks like from the inside. Not a dramatic clash of theories. One group with a persistent signal, everyone else unable to reproduce it, and no agreed path to settling it. Meanwhile, the searches continue downward, and they are approaching a hard limit that cannot be engineered away. It is called the neutrino fog, and it used to be called the neutrino floor. Neutrinos are produced in enormous quantities by nuclear fusion in the Sun, by cosmic rays hitting the atmosphere, and by supernovae throughout the galaxy. Most pass through any detector without interacting, but at very low energies, a neutrino can scatter coherently off an entire nucleus rather than off individual particles inside it, a process predicted in the 1970s and finally observed in 2017. That interaction produces exactly the signal a WIMP would produce, a nuclear recoil of a few thousand electron volts in the fiducial volume with the correct signal ratio. There is no way to tell them apart on an event-by-event basis. Once detectors become sensitive enough to see solar neutrinos scattering this way, they acquire an irreducible background that mimics the thing they are hunting. Progress does not stop, but it slows dramatically. Every further improvement requires far more exposure to distinguish a small signal from a background that looks identical. That threshold lies perhaps 1 or 2 orders of magnitude below current limits. The largest xenon experiments now running are expected to begin encountering it within the next several years. Beyond it, distinguishing dark matter from neutrinos requires knowing which direction the recoiling nucleus traveled, because the neutrino background comes predominantly from the Sun, while the dark matter wind comes from Cygnus. Building a detector that can reconstruct the direction of a recoil a few thousand electron volts in energy is an extremely difficult technical problem. Several groups are working on it, using low-pressure gas targets where recoil tracks are long enough to image. So the WIMP era is not over, but its confident phase has ended. The elegant version failed to appear. There is an obvious objection to everything just described, though, and it is worth taking seriously. All of it assumes the particle comes to us, that it wanders into a tank of xenon under a mountain and happens to strike a nucleus in the quiet center of it. That is a passive strategy. There are 2 others, and both were pursued at the same time, at enormous expense, by entirely different communities. One of them tried to manufacture the particle. The other went looking for the places in the galaxy where dark matter should be destroying itself. There are 3 ways to find a particle, and the underground detectors are only one of them. The first is to catch it passing through, which is what the xenon tanks attempt. The second is to make it. The third is to watch for it destroying itself somewhere out in the galaxy and read the wreckage. Making it was the job of the Large Hadron Collider, and the way the search works there is worth understanding because it is so unlike what most people picture. You do not detect a dark matter particle at a collider. It would sail straight out through the entire detector, through the silicon trackers, through the calorimeters, through the muon chambers, through the iron and the concrete without leaving a mark, exactly as it sails through the Earth. What you detect is its absence. In a proton-proton collision, momentum has to balance. The 2 beams come in along the axis of the machine, so the total momentum, perpendicular to the beam, before the collision is 0. Afterwards, if you add up the momenta of everything that came out, the perpendicular components must still sum to 0. If they do not, if all the visible debris is flying off to one side, unbalanced, then something invisible went the other way, carrying momentum with it. Physicists call this missing transverse energy, and it is the signature of anything that escapes undetected. Neutrinos produce it routinely, and their contribution can be calculated and subtracted. Any excess beyond that would be new. The classic search looks for a single jet of ordinary particles recoiling against nothing at all. A quark is knocked out of the collision, produces a spray of hadrons, and flies off in one direction with nothing balancing it. It is called a monojet event, and it is exactly what you would see if a pair of dark matter particles were produced and left the building. Detectors at the Large Hadron Collider have been running these searches since 2010. Across every increase in energy and luminosity the machine has delivered, they have found no significant excess. Nor have the searches for supersymmetric particles that would produce dark matter as a decay product searches, which have pushed the lower mass limits on those particles up by roughly a factor of 5 over the last 15 years, well past the range that the original theoretical arguments favoured. The absence at the collider matters in a particular way. Collider searches are relatively insensitive to how a particle scatters off a nucleus, so they cover regions of parameter space the underground detectors handle poorly, especially at low masses. The 2 approaches close different doors. Both are now closed across most of the region where the elegant version of the theory lived. The third approach is the one that looks outward, and it is called indirect detection. The logic runs back to the thermal relic calculation. If dark matter particles were produced in the early universe and reduced to their present abundance by annihilating with each other, then that annihilation process has not switched off. It has only become rare because the particles are now spread thinly and seldom meet, but they are not spread evenly. In the densest places, the center of the Milky Way, the cores of dwarf galaxies, the middle of a cluster, the density is high enough that collisions should still occur at a measurable rate. When two dark matter particles annihilate, whatever they produce must eventually decay into ordinary matter and radiation. Gamma rays, positrons, antiprotons, neutrinos, all of these are detectable, and the gamma rays are the most useful because they travel in straight lines and point back at their source. So astronomers look at the galactic center and ask whether there is more high-energy gamma radiation coming from it than known sources can explain. The instrument doing most of this work is the Fermi Gamma Ray Space Telescope, launched in 2008 into low Earth orbit. It surveys the entire sky every 3 hours, building up a continuous map of the universe at photon energies millions of times higher than visible light. And in the region around the center of our galaxy, it sees something that nobody has been able to explain away. It was first identified around 29 and has been studied continuously since. After subtracting the known contributions cosmic rays striking interstellar gas, individual identified sources, the diffuse emission from the disk, a residual glow remains. It is roughly spherically symmetric around the galactic center, extending outward for perhaps a few thousand light years. Its brightness falls off with distance from the center in a way that closely resembles the expected shape of a dark matter halo, and its energy spectrum peaks in the region of a few billion electron volts. That is remarkably close to what a WIMP of a few tens of proton masses, annihilating at roughly the rate the thermal relic calculation predicts, would produce. For a while, this looked like it might be the discovery. The difficulty is that the center of the galaxy is the most complicated region in the sky. It contains a supermassive black hole, dense molecular clouds, intense magnetic fields, star-forming regions, supernova remnants, and an enormous population of stars, all overlaid on a line of sight that passes through the entire thickness of the galactic disk. The leading alternative explanation is millisecond pulsars-old neutron stars spun up to rotation periods of a few thousandths of a second by material pulled from a companion, which emit gamma rays with a spectrum very similar to the one observed. A large, unresolved population of them in the galactic bulge would produce a diffuse glow of exactly this kind. The argument between these two explanations has run for over a decade and has turned on subtle statistical questions about whether the emission is genuinely smooth or is made of many faint point sources blurred together. Different analysis techniques have given different answers. Some studies found evidence for point source structure. Others found the evidence disappeared when the model of the background emission was changed. It remains unresolved, and it is a good illustration of a general difficulty with indirect detection. The interesting places are the messy places, because density is what makes both signals and confusion, which is why the strongest constraints come from somewhere quieter. The dwarf spheroidal galaxies orbiting the Milky Way are the cleanest dark matter laboratories available. They are close, they contain very few stars, they have almost no gas, no star formation, no supernova remnants, and no known sources of high-energy gamma rays whatsoever. And their internal motions show they are overwhelmingly dominated by dark matter, in some cases by a factor of several hundred. If dark matter annihilates, these objects should glow faintly in gamma rays and nothing else should be coming from them. The Fermi telescope has stared at dozens of them for years and combined the observations statistically. It has seen nothing. That non-detection now excludes the simplest thermal relic annihilation rate for particles below roughly 100 proton masses, which is to say, it cuts directly into the region the WIMP miracle pointed at. There have been other candidate signals, and the pattern by now is familiar. The Alpha Magnetic Spectrometer, mounted on the outside of the International Space Station since 2011, measures cosmic ray particles arriving at Earth. It confirmed an unexpected excess of positrons, the antimatter counterpart of the electron, rising with energy above about 10 billion electron volts. Dark matter annihilation would produce positrons, and this was greeted with considerable excitement. But so would nearby pulsars, which are known to accelerate electrons and positrons to high energies, and there are several within a few thousand light-years. Later measurements of the spectral shape and of gamma-ray halos around two nearby pulsars have made the pulsar explanation increasingly favoured. The excess is real. Its origin is almost certainly ordinary. The same instrument has reported a possible excess of antiprotons in a similar energy range, which has been argued about along similar lines, with the uncertainty dominated by how cosmic rays propagate through the galaxy's magnetic field rather than by the measurement itself. And there is one more channel, which is the strangest of the set. The Sun sweeps through the dark matter halo continuously. Occasionally, a dark matter particle passing through the Sun will scatter off a nucleus, lose energy, and fail to escape. Over billions of years, such particles would accumulate in the solar core, gradually concentrating until the density is high enough that they annihilate with each other at a steady rate. Almost everything produced by those annihilations would be absorbed immediately by the Sun, except neutrinos, which pass out through the entire star without difficulty. So a neutrino detector on Earth can look at the Sun and ask whether there is an excess of high-energy neutrinos coming from its core neutrinos, far more energetic than anything nuclear fusion produces. The IceCube Observatory does exactly this. It consists of a cubic kilometre of Antarctic ice at the South Pole, instrumented with 5,000 light sensors on strings lowered into holes melted down to 2.5 kilometres. The ice itself is the detector. A neutrino interacting anywhere within it produces a charged particle travelling faster than light does in ice, which emits a cone of blue light that the sensors record, allowing the direction of the original neutrino to be reconstructed. Pointing that back at the Sun and looking for an excess produces some of the strongest limits available on how strongly dark matter can interact with hydrogen, in particular a constraint that is complementary to the xenon detectors, which are far more sensitive to heavy nuclei. No excess. Again, 3 approaches. Make it, catch it, watch it, annihilate. Decades of effort in each, every result consistent with 0. None of this proves dark matter is not a particle. Null results never prove absence. They only move boundaries. And there are entirely reasonable particles that would produce no signal in any of these searches, particles that do not annihilate at all, or that interact so feebly that no conceivable detector would register them, or that sit at masses these techniques cannot reach. But the specific, elegant, theoretically motivated version, the one that connected dark matter to the structure of particle physics, that arrived with the WIMP miracle attached and made 3 independent kinds of experiment worth building, has been searched for across the range where it was expected, and it was not there, which pushed the field toward a candidate that had been sitting in the literature since 1977, proposed for reasons that had nothing to do with astronomy, by physicists trying to fix an entirely different embarrassment. The strong nuclear force has a problem that nobody asked it to have. It is the force that binds quarks into protons and neutrons, and binds protons and neutrons into nuclei, and it is described by a theory called quantum chromodynamics. That theory works. It has survived every experimental test applied to it for 50 years. But written into its equations is a term that should produce an observable effect, and the effect is not observed. The term concerns a symmetry called charge parity symmetry, or CP for short, the combination of 2 operations. Charge conjugation swaps every particle for its antiparticle. Parity reflects space, turning left into right, as a mirror does. Apply both, and ask whether the laws of physics look the same. For most interactions, they do. The weak nuclear force violates the symmetry, which was discovered in 1964 in the decay of certain particles called kaons, and which is one of the ingredients needed to explain why the universe contains matter and not equal parts matter and antimatter. The strong force, by contrast, appears to respect the symmetry exactly. The awkwardness is that the equations of quantum chromodynamics contain a parameter, an angle, conventionally written as theta, that controls how strongly the strong force violates CP symmetry. There is no theoretical reason for it to take any particular value. It could be anything between 0 and about 6. If it were not essentially 0, the neutron would have an electric dipole moment. It would have a slight separation of positive and negative charge along an axis, making it very slightly like a tiny bar magnet, but for electricity, and this would be measurable. Experiments have been searching for the neutron's electric dipole moment since the 1950s, with steadily improving precision. They have never found it. The current limit implies that theta is smaller than about 10 to the power of -10, a parameter that could naturally be anything, measured to be smaller than 1 part in 10 billion. Physicists do not like this, and the reason is not aesthetic prejudice. In physics, quantities that are unnaturally small usually turn out to be small for a reason, some symmetry or mechanism enforcing it. An unexplained near zero is usually a clue that something is missing from the theory. In 1977, Roberto Pecce and Helen Quinn at Stanford proposed a mechanism. Instead of theta being a fixed number written into the laws of nature, let it be a dynamical field, something that can vary and evolve, and that has a lowest energy state. Then, like a ball rolling into a valley, theta would naturally settle to zero on its own, regardless of where it started. The mechanism works, but new dynamical fields in quantum field theory come with an unavoidable consequence. They have excitations, and excitations are particles. Frank Wilczek and Steven Weinberg independently realized this within months. The Pecce-Quinn mechanism necessarily implies a new particle, light, electrically neutral, and interacting extraordinarily weakly with everything. Wilczek named it the axion. He took the name from a brand of laundry detergent, on the grounds that the particle cleaned up a problem. Nobody at the time was thinking about dark matter. It was some years before anyone noticed that this particle, invented to fix an unrelated puzzle in nuclear physics, happened to satisfy the entire astronomical specification. The axion's properties are unlike a WIMP's in almost every respect. It is astonishingly light. Astrophysical constraints and theoretical arguments place its mass somewhere between roughly a millionth and a thousandth of an electron volt, which makes it something like 1 billion times lighter than an electron and perhaps 100,000 billion times lighter than a WIMP. Because it is so light, the number required to account for the dark matter density is staggering. If axions are what fills the halo, then something on the order of 100 trillion of them are passing through every square centimetre of your body every second. So many, and so light, that they do not behave like a swarm of particles at all. They behave like a field, a coherent oscillation, more like a wave than a collection of objects, filling all of space and vibrating at a frequency set by the axion mass. The dark matter, in this picture, is not a fog of tiny bullets. It is a standing hum. The axion also could not have been produced the way a WIMP would have been. It interacts far too weakly to have ever been in thermal equilibrium. Instead, it would have been created by a process called vacuum misalignment. In the very early universe, the axion field would have been sitting at some arbitrary value, not at its minimum. As the universe cooled and the strong force switched on properly, the field would have begun to roll toward its minimum, overshoot, and oscillate. Those oscillations carry energy, and the energy behaves exactly like cold, pressureless matter, which is precisely what dark matter must be. Calculate the relic density from that process for plausible values of the axion mass, and you get roughly the observed dark matter abundance. It is a second miracle, arriving from a completely different direction than the first one. Finding it is the difficulty. The axion's one useful property is that in a strong magnetic field it can convert into a photon. The conversion is extremely improbable, but it is not zero, and it is the basis of essentially every axion search ever attempted. The axion dark matter experiment at the University of Washington is the most mature of them. At its heart is a resonant microwave cavity, a precisely machined metal chamber sitting inside a powerful superconducting magnet and cooled to a fraction of a degree above absolute zero. If halo axions passing through that cavity convert into photons, the photons produced will have a specific frequency determined by the axion's mass. And if the cavity happens to be tuned to resonate at exactly that frequency, the signal builds up inside it and becomes detectable. Slightly off resonance and there is nothing. So the experiment scans. Movable rods inside the cavity change its resonant frequency in tiny steps, and at each step the experiment listens for a fraction of an hour before moving on. It is, precisely and literally, tuning a radio through a band, waiting for a station. The problem is the size of the band. The axion mass is unknown across roughly 3 orders of magnitude, and the cavity technique only works efficiently over a limited range of frequencies at a time. The experiment has been running in various forms since the 1990s and has excluded a meaningful slice of the most theoretically favoured region. It has not found the axion. The signal it is listening for, incidentally, would be a power of around 10 to the power of minus 23 watts. For scale, the total energy collected by every radio telescope on Earth over the entire history of radio astronomy, from all cosmic sources combined, is often quoted as less than the energy of a falling snowflake. Other searches use different geometries. The Axion telescope at CERN takes a prototype magnet built for the Large Hadron Collider, mounts it on a platform that can track the Sun, and looks for axions produced in the solar core, converting to X-rays as they cross the magnetic field. The advantage is that the Sun would be a bright axion source, regardless of whether axions are the dark matter. The disadvantage is that solar axions arrive with much higher energies, and the sensitivity is different. Then there is the technique known as light shining through a wall, used by experiments in Germany and elsewhere. Fire an intense laser through a magnetic field. A tiny fraction of photons may convert to axions. Axions pass straight through a solid barrier placed in the beam because they interact with essentially nothing. On the far side, another magnetic field converts a tiny fraction of them back into photons. The signal is a faint glow appearing on the dark side of a wall that light cannot cross. So far, the wall has stayed dark. Newer approaches are proliferating rapidly because the field has realized the search space is enormous and the cavity technique cannot cover it alone. There are experiments using nuclear magnetic resonance, looking for axions inducing tiny oscillating spins in samples of material. There are experiments using dielectric layers to enhance conversion. There are proposals using superconducting circuits and quantum sensors that can count individual microwave photons, which is now possible with technology developed for quantum computing. The axion is currently the most actively pursued candidate in the field, and the reason is straightforward. It is the only proposal that solves an independent problem in fundamental physics and happens to work as dark matter as a side effect. That is exactly the pattern that has been productive historically. It is how the neutrino was found, and the Higgs boson, and the positron. But it is not the only alternative, and the space of possibilities has grown considerably as the WIMP searches have come up empty. Sterile neutrinos are one. The three known types of neutrino interact through the weak force. A sterile neutrino would not. It would interact only through gravity and through mixing with ordinary neutrinos. Such a particle would be produced in the early universe in the right abundance if its mass were in the region of a few thousand electron volts. It would also be slightly unstable, occasionally decaying and emitting an X-ray photon at a characteristic energy, which makes it testable. In 2014, two groups reported an unexplained X-ray emission line at around 3,500 electron volts in the spectra of galaxy clusters, and there was considerable excitement that this might be exactly that decay. Subsequent observations, including deep exposures of objects where the line should have been strongest, have not confirmed it, and most of the field now regards it as likely instrumental or atomic in origin. Primordial black holes are another. These would not be the black holes formed by collapsing stars, which are made of ordinary matter and therefore ruled out by the deuterium argument. These would have formed in the first fractions of a second after the Big Bang, from density fluctuations so extreme that regions collapse directly. Such objects would be non-baryonic in the accounting that matters, because they formed before nucleosynthesis. The idea has been around since the 1970s and received renewed attention after the first gravitational wave detections revealed black holes somewhat heavier than expected. But microlensing surveys monitoring millions of stars in the Magellanic Clouds and the galactic bulge for the brief brightening that occurs when a compact object passes in front of one have excluded most of the mass. Range. A few narrow windows remain open. Then there are the more exotic proposals, each with its own community. Fuzzy dark matter posits particles so light around 10 to the power of minus 22 electron volts that their quantum wavelength is measured in thousands of light years. At that scale, quantum mechanics operates across an entire galaxy. The dark matter would form an interference pattern, with a dense standing wave core at the center of each halo and granular structure throughout, which would suppress the formation of the smallest structures in a way that might be observable. Self-interacting dark matter allows the particles to scatter off one another, though not off ordinary matter. This would let halos redistribute energy internally, smoothing out their centers over billions of years. Dark photons propose an entire hidden sector, a parallel set of forces and particles, interacting with our sector only through some very weak coupling, of which dark matter would be merely the most abundant component. In the most elaborate versions, there could be dark chemistry, dark atoms, even a thin dark disk running through our galaxy. That last idea is worth noting mostly as a measure of how open the question is. There is no evidence for it. There is also no way, at present, to rule out most of it. The theoretical space has become enormous, which is what happens to a field when its most compelling candidate fails to appear. Instead of one target and one technology, there are dozens of targets and dozens of small experiments, each probing a different corner. Some physicists find this healthy and natural broadening after a premature narrowing. Others find it uncomfortable, because a field with 100 candidates and no signal is a field that could stay in that condition indefinitely. And there is a third position, held by a small but persistent minority, which has been present since the beginning, and which the failure of the direct searches has made harder to dismiss out of hand. It holds that the reason nobody has found the particle is that there is no particle. In 1983, a physicist at the Weizmann Institute in Israel, named Mordechai Milgrom, published 3 papers in the same issue of a journal, laying out a single idea from 3 directions. Milgrom was not trying to be provocative. He had been looking at rotation curves, the flat curves Rubin and Bosma had established, and asking a narrow question. Is there a pattern in where the discrepancy appears? The obvious guess would be that the discrepancy appears at large distances. Gravity weakens with distance, so if something is wrong with gravity, it should show up far from the center. Milgrom found that distance was not the right variable. What predicted the onset of the anomaly was not how far out you were, but how weak the local gravitational acceleration had become. Different galaxies of very different sizes started showing flat rotation at very different radii, but all of them started showing it at roughly the same acceleration. That number is about 10 to the power of minus 10 meters per second per second. It is difficult to overstate how small that acceleration is. Release an object under it, and it would take about 3 hours to fall 1 meter. It is roughly 100 billion times weaker than the gravity you are experiencing right now. Milgrom's proposal was that below that threshold, the law of motion changes. In Newtonian mechanics, force equals mass times acceleration, and the gravitational force between 2 masses falls with the square of the distance between them. Combine those, and you get orbital velocities that decline as the square root of distance the falling curve every spiral galaxy fails to display. In modified Newtonian dynamics, or MOND, that relationship holds exactly at ordinary accelerations. In the solar system, on Earth, in binary star systems, in the orbit of a spacecraft, nothing changes at all. But when the acceleration falls below the critical value, the relationship shifts. The effective force falls off more slowly with distance. And the mathematical consequence is that the orbital velocity at large radius stops declining and becomes constant. A flat rotation curve with the constant velocity determined entirely by the total ordinary mass of the galaxy. That is the theory. One new constant, applied everywhere, and no invisible substance at all. Its record at the scale of individual galaxies is genuinely impressive, and this is the part that is often skipped over by people who have already decided the question. MOND does not merely reproduce flat rotation curves in general. Given the distribution of visible stars and gas in a particular galaxy from a photograph and a radio map, with no free parameters beyond the mass-to-light ratio of the stellar population, it predicts the detailed shape of that galaxy's rotation curve, including the bumps and wiggles where spiral arms and gas rings sit. And the predictions match galaxy after galaxy across a range of masses spanning 5 orders of magnitude. More striking is the relation it explains without effort. Astronomers have long known that in spiral galaxies, the total mass of stars and gas predicts the asymptotic rotation velocity with remarkably little scatter. This is the baryonic Tully-Fisher relation, and it holds across dwarf galaxies and giants alike, tighter than the observational uncertainties in many samples. In the dark matter picture, this relation is a coincidence that has to be arranged. The rotation velocity at large radius is set by the dark halo, and the visible mass is set by how efficiently that halo turned gas into stars, a messy process involving cooling, star formation, supernova winds, and black hole feedback. There is no obvious reason those two independent quantities should track each other so precisely. Modern simulations do reproduce the relation, but they reproduce it as an outcome of calibrated feedback physics, rather than deriving it. In MOND, the relation is not an outcome, it is an identity. It falls directly out of the modified force law with no adjustment available. There is nothing to tune. MOND also made predictions in advance that turned out correct. The most notable concerns low surface brightness galaxies diffuse, faint spirals with their stars spread thinly. In the dark matter framework, there is no particular reason such galaxies should behave distinctively. In MOND, because their internal accelerations are low everywhere, they should show large discrepancies from Newtonian expectation all the way into their centers. When such galaxies were systematically observed in the 1990s, they did. That is a genuine successful prediction, made before the data existed, by a theory most of the field regarded as wrong. So why does most of the field still regard it as wrong? Because the universe contains more than individual spiral galaxies, and above that scale, MOND runs into difficulties that have not been resolved in 40 years. The first is clusters. Apply MOND to a galaxy cluster, using the hot X-ray gas to measure the mass distribution, and the discrepancy shrinks but does not disappear. A factor of 2 or 3 of unseen mass remains. Most MOND advocates accept this and propose that clusters contain some genuinely undetected ordinary matter, or perhaps massive neutrinos, which is to say, the theory that was proposed to eliminate dark matter requires dark matter in clusters. It is a partial solution, and its partialness is the central difficulty in defending it as fundamental. The second is the bullet cluster and its relatives, for the reasons already discussed. A force law sourced by visible matter has considerable trouble producing gravitational mass that has walked away from the visible matter. The third, and the most serious, is cosmology. MOND, as Milgrom wrote it, is a modification of Newtonian mechanics, which means it is non-relativistic, which means it cannot be applied to the expanding universe at all. To handle cosmology, you need a relativistic theory. Jacob Bekenstein constructed one in 2004, and others have followed, but these theories work by adding extra fields to general relativity. And once you have added extra fields, carrying energy and shaping gravity on large scales, the distinction between a modified force law and an invisible substance becomes considerably less clear than it first appeared. More concretely, these theories have struggled to reproduce the cosmic microwave background power spectrum. The relative heights of the acoustic peaks require a component that does not oscillate with the plasma, and it is difficult to produce that with a field that couples to ordinary matter. Some recent relativistic extensions claim to fit the peaks, at the cost of considerable complexity and additional fields. Whether that counts as a modified gravity theory or a dark matter theory wearing different clothes is, at that point, close to a question of terminology. The honest summary is this: MOND is the best description we have of the dynamics of individual galaxies. Cold, dark matter is the best description we have of everything larger. Neither works well in the other's domain. 40 years of argument has not changed that, and both camps have grown accustomed to explaining away the other's strongest evidence. And the standard picture has its own unresolved problems, which do not get discussed nearly as often outside the field. They live at small scales, and they have been a persistent source of tension since the 1990s. The first is the missing satellites problem. Simulations of cold dark matter predict that a halo the size of the Milky Way's should contain hundreds, possibly thousands, of smaller subhalos orbiting within it dense clumps left over from the merging process, each in principle capable of hosting a small galaxy. When the problem was first posed, only about a dozen satellite galaxies of the Milky Way were known. The mismatch was an order of magnitude or more. This one has largely, though not entirely, dissolved, and the way it dissolved is instructive. Deep surveys have since found far more satellites, because most of them are extraordinarily faint. The Sloan Digital Sky Survey, and then the Dark Energy Survey, turned up dozens of ultra-faint dwarf galaxies, some containing only a few hundred stars, so dim that they were identified as slight statistical overdensities of stars, rather than as objects anyone could see. Segway 1, discovered in 2006, contains perhaps 1,000 stars, and yet its internal motions imply a mass several hundred times greater than its light. The highest mass-to-light ratio measured for any galaxy, and one of the cleanest demonstrations that dark matter dominates the smallest systems most completely. Meanwhile, simulations that include the physics of gas rather than gravity alone show that the smallest subhalos should mostly fail to form stars at all because ultraviolet radiation from the first generation of stars heated intergalactic gas enough to prevent it collapsing into the shallowest wells. The counts now roughly agree, within the considerable uncertainties. It was a real problem, and it was resolved by better observations and better physics rather than by abandoning the framework. The second problem is more stubborn. It is called the cusp core problem. Dark matter-only simulations produce halos with density rising steeply toward the center, the cusp described by Navarro, Frank, and White. But when astronomers measure the internal structure of dwarf galaxies, mapping rotation at very small radii, using high-resolution spectroscopy of gas and individual stars, the data persistently prefer a core, a central region where the density flattens out rather than continuing to rise. Dwarf galaxies are the cleanest test cases available because they are dark matter dominated all the way to their centers, and there is little ordinary matter to confuse the measurement, and they keep saying core. There are two families of explanation. The first is that the simulations are missing physics specifically, the effect of ordinary matter. When gas falls to the center of a small galaxy and forms stars, and those stars explode as supernovae, the resulting outflows can move a significant mass of gas outward rapidly. Do that repeatedly over billions of years, and the gravitational potential at the center fluctuates, and each fluctuation transfers a little energy to the dark matter particles, which drift outward. Enough cycles and a cusp is flattened into a core. Simulations, including this effect, can produce cores, though the result depends sensitively on how star formation and feedback are modeled, which is the least certain part of the calculation. The second family holds that the cores are telling us something about dark matter itself, that it is warm rather than cold, or that it interacts weakly with itself, or that it is fuzzy. Each of these would naturally produce cores, and each makes additional predictions that can be tested against the abundance and structure of small galaxies. The question is genuinely open. It is one of the few places where the small-scale distribution of dark matter might reveal something about the particle rather than merely confirming its presence. And then there are the objects that should not exist under either framework. In 2018, a team led by Peter van Dokkum at Yale reported observations of a diffuse ghostly galaxy in the constellation Cetus, roughly the size of the Milky Way, but containing a few hundred times fewer stars. They measured the motions of the globular clusters orbiting within it, and found the velocities to be extremely low, consistent with the visible stars providing all the mass. A galaxy, apparently, with essentially no dark matter. For the standard picture, this is odd but survivable. Dark matter can in principle be stripped from a galaxy by a close encounter with a larger one, and there is evidence this galaxy has had such an encounter along with a second nearby galaxy in the same condition. For MOND, it is far more awkward. In MOND, the low internal accelerations of such a diffuse galaxy would guarantee a large apparent mass discrepancy. There is no way to strip a force law. The predicted velocities are substantially higher than the measurements. There have been vigorous arguments about the distance to the galaxy, which affects everything, and about the reliability of measuring velocities from a small number of globular clusters. The dispute is not settled. A galaxy with too little dark matter is, in its way, a stronger argument for dark matter being a substance than a galaxy with too much. Something you can remove is a thing. A modified law of nature travels with the object and cannot be taken away. That is where the debate sits, not as a clean contest between a right answer and a wrong one, but as two frameworks, each explaining a domain the other struggles with, each accumulating anomalies, and neither able to deliver the single decisive observation that would end it. What would end it, of course, is finding the particle, and after 90 years of increasingly precise measurement and 40 years of increasingly sensitive searching, the situation has arrived at something genuinely unusual in the history of science. We know the density of dark matter in the universe to about 1%. That is a better figure than we have for the mass of the Earth's atmosphere, or the total volume of water in the oceans, or the number of trees on the planet. It is a better figure than the mass of the electron was known to for most of the 20th century. We know how it is distributed, at every scale from the interior of a dwarf galaxy to the largest filaments of the cosmic web. We know its distribution in 3 dimensions across a substantial fraction of the observable universe, mapped by weak lensing surveys measuring the shapes of hundreds of millions of galaxies. We know how that distribution has evolved over the last 10 billion years, because looking further away means looking further back, and the maps can be sliced by distance. We know it was already present in the first minutes after the Big Bang. We know it is cold, collisionless, neutral, non-baryonic, and stable across the entire history of the universe. We know it does not interact with light at any level any instrument has been able to detect, across the full electromagnetic spectrum, from radio to gamma rays. We know that without it the galaxies would not have formed, and that the ones that did form would have destroyed themselves. And we do not know what it is, not roughly, not within a factor of 1,000. We do not know its mass to within 30 orders of magnitude, which is the range currently spanned by serious candidates from ultralight fields with galaxy-sized wavelengths to primordial black holes weighing as much as an asteroid. This combination is what makes the problem so unlike most open questions in science. It is not a vague anomaly waiting for better data. The data is exquisite. It is a precisely specified absence. It is worth putting the 90 years in context, because there is a tendency to treat a long, unsolved problem as a symptom that something has gone wrong, and the history does not support that. Wolfgang Pauli proposed the neutrino in 1930, in a letter to a physics conference he did not attend because he had a dance to go to. He apologized in the letter for inventing a particle that could not be detected. It was directly detected in 1956, 26 years later, by Clyde Cowan and Frederick Rines, using a nuclear reactor as the source. The Higgs boson was proposed in 1964 by several groups working independently. It was confirmed at the Large Hadron Collider in 2012, 48 years. Gravitational waves were predicted by Einstein in 1916, and he spent decades uncertain whether they were physically real or an artifact of the coordinates. The first direct detection came in 2015, 99 years later, when 2 detectors in Louisiana and Washington state recorded a signal lasting 1/5 of a second from 2 black holes merging over 1 billion light-years away. Continental drift was proposed in 1912 and rejected for 50 years, until seafloor magnetic surveys in the 1960s supplied a mechanism. 90 years is not an anomaly. It is roughly the normal duration of a genuinely hard question in physics. What makes dark matter unusual is not the length of the wait, it is the proportion of the universe involved. Pauli's neutrino was one particle among many, and getting it wrong would have left the rest of physics standing. This is most of the matter in existence. Everything in the periodic table, everything built from it, every star, every planet, every organism that has ever lived, all of it is the minority component, the 15%, the part that happens to give off light, and therefore happens to be the part we noticed first. There is a reasonable expectation that the next 20 years will resolve it, and there is a reasonable expectation that they will not. The instruments are arriving regardless. The Vera Rubin Observatory on Cerro Pachon in Chile has an 8.4-meter mirror and a camera of 3.2 billion pixels, the largest digital camera ever constructed for astronomy. It will photograph the entire visible southern sky every few nights for 10 years, producing a time-lapse film of the universe and a weak lensing dataset covering billions of galaxies. It will map the distribution of dark matter across cosmic time, with a precision nothing before it has approached. The European Space Agency's Euclid telescope, launched in 2023 and now operating at a point beyond the Earth's orbit where it can stay permanently shaded, is doing the same from space, where there is no atmosphere to blur the galaxy shapes that weak lensing depends on. It will survey 1/3 of the sky. And, underground, the xenon detectors continue scaling. Proposals exist for detectors holding tens of tons, which would push the sensitivity down until they hit the neutrino fog. Directional detectors, which could see past that limit by measuring which way a struck nucleus recoils, are in development. The axion searches are broadening fastest of all, borrowing quantum sensing technology developed for computing to detect individual microwave photons, and covering mass ranges that were inaccessible a decade ago. And there are entirely new channels opening. Gravitational wave observatories can constrain primordial black holes by counting mergers, pulsar timing arrays. CHEM, which watch the arrival times of pulses from rapidly rotating neutron stars across the galaxy with nanosecond precision, are sensitive to dark matter passing through the intervening space. The James Webb Space Telescope, by finding the earliest galaxies, is testing when structure could first have assembled, which constrains how cold the dark matter had to be. Any one of these could produce the answer. So could an experiment nobody has thought of yet, which is roughly how the microwave background was found, and the first gravitational lens, and the cosmic ray showers that started particle physics. Or the answer may simply not arrive on our schedule. There is no rule requiring a question to be solved within the working life of the people asking it. Let us go back to the room. You are lying somewhere at some hour, in some country whose name I do not know. The room may be dark, or it may not be. It does not matter. The dark matter is passing through you either way. If it is made of the heavy particles, then something like 1 million of them cross through your body every second. If it is made of axions, then it is not really a stream of particles at all, but a field, a slow, coherent oscillation filling the room and the building and the sky, humming at a frequency nobody has yet managed to tune to. They come from the direction of Cygnus, because that is the way the solar system is heading through the halo, and they are moving at a few hundred kilometers per second, and they pass through the ceiling, and through you, and through the mattress and the floor, and the rock beneath the foundations, and down through the mantle, and through the iron core of the planet, and out the other side into space, having noticed none of it. To them, the Earth is not solid. It is a faint gravitational dimple, and they fall through it without registering that anything was there. That flow has been continuous for your entire life. It was continuous before there was a planet here for it to pass through. We have weighed it in the motions of 1,000 galaxies in Coma Berenices. We have watched it hold spiral arms in shape for billions of years past the point where they should have collapsed. We have seen it bend the light of galaxies behind it into arcs and rings. We have watched it walk away from its own atoms in the wreckage of 2 clusters colliding. We have read its weight in the 3rd acoustic peak of the oldest light in existence, printed there when the universe was 380,000 years old and has been travelling ever since. We have built the quietest rooms on Earth, under mountains, out of Roman lead and copper grown atom by atom in the dark, and we have sat in them and waited, and nothing has arrived. 85% of the matter in the universe, measured, mapped, weighed, traced, across 13.8 billion years. Unidentified, the experiments are still running tonight. Somewhere under the Apennines, a tank of liquid xenon is being watched by an array of light detectors that would register a single ultraviolet photon. Somewhere in South Dakota, 1.5 miles underground in an old gold mine, another one. In Washington state, a microwave cavity in a magnet cooled to a fraction of a degree above absolute zero is scanning slowly through frequency, listening for a tone. In Chile, a very large camera is photographing the southern sky, one field at a time, all night, every night. None of them may find anything this year. Someone may find something tomorrow. The room is quiet. The particles are moving through it at 300 kilometers per second, as they have for the whole history of the Earth, and they will still be moving through it long after the question is either answered or abandoned. Good night.